Look up at the night sky on a clear evening, and you'll see a vast, dark canvas dotted with distant points of light. It's easy to forget that between those twinkling stars and glowing planets, our solar system is filled with countless silent wanderers, asteroids, tumbling through the emptiness, remnants from the very dawn of our cosmic neighborhood. For centuries, we saw them as little more than simple rocks, inert and unchanging. But what if we've been underestimating them all along? What if these ancient, pockmarked travelers hold secrets so bizarre, so utterly unexpected, that they could rewrite our understanding of the cosmos itself? That quiet rock drifting millions of miles away might not be a barren wasteland at all, but a locked chest, and scientists are only just now beginning to find the keys. This is a journey to the frontier of discovery, a dive into the truly weird and wonderful things researchers have uncovered when they've trained their most powerful instruments on these nomadic space objects. We're about to explore 25 of the most bizarre things scientists have found on asteroids, findings that range from the head-scratching to the revolutionary. Imagine a world where metal flows in rivers, where the building blocks of life itself are scattered like cosmic confetti, and where materials thought to be incredibly rare on Earth are found in staggering abundance. The old image of a dull, gray lump of rock is shattered forever when you learn what's actually hiding in plain sight, just waiting to be found. So, get ready for an adventure that will challenge everything you thought you knew about our solar system's smallest inhabitants. We're not just talking about craters and dust. We're talking about discoveries that hint at ancient oceans, that suggest the possibility of resources that could power our future, and that even raise profound questions about our own origins. This is a story of scientific curiosity meeting cosmic chance, a tale pieced together from data beamed back by intrepid spacecraft and powerful telescopes. The journey into the strange begins now, as we count down 25 of the most bizarre, mind-bending, and utterly fascinating things ever found on an asteroid. Starting our countdown at number 25, we encounter a discovery that completely upended one of our most basic assumptions about the solar system: the presence of water ice. For the longest time, the conventional wisdom was that asteroids, being so close to the sun and lacking any meaningful atmosphere, were simply baked dry, their surfaces rendered completely barren by the relentless heat of stellar radiation. They were the ultimate deserts of space, but science has a wonderful habit of proving our assumptions wrong. The first major clues came not from a single mission, but from years of telescopic observation, where astronomers began to notice a telltale signature in the light reflecting off certain asteroids, particularly those in the main belt between Mars and Jupiter. This signature, a specific dip in the infrared spectrum, was a clear indicator of water molecules. The implication was staggering. These weren't just dry rocks. Some of them were actually storing water, likely preserved as ice just beneath a layer of protective dust and rubble. This discovery of water ice doesn't just add a new item to a catalog of asteroid features. It fundamentally reshapes two of the biggest stories in science: the story of our own past and the story of our future. Let's start with the past. One of the most enduring mysteries on Earth is how our beautiful blue planet, seemingly unique in the inner solar system, got all of its water. The early Earth was a molten, violent place, and any original water would have likely been boiled away into space. So where did our oceans come from? For decades, the leading theory has pointed the finger at comets, those icy wanderers from the outer solar system, but the chemistry didn't always perfectly match. The finding of water-rich asteroids opens up a compelling new chapter in this ancient detective story. It suggests that a significant portion of Earth's life-giving water could have been delivered not by distant comets, but by these far more local and numerous asteroids, bombarding our young planet and literally filling our basins. These silent, tumbling rocks may very well have been the couriers that brought the very essence of life to our world. Now, let's pivot from our ancient history to our potential future. Finding water ice on asteroids transforms them from mere objects of scientific curiosity into potentially the most valuable pieces of real estate in the solar system. Water out there isn't just for drinking. Through a relatively straightforward process called electrolysis, it can be split into its core components, hydrogen and oxygen. Oxygen, of course, is essential for astronauts to breathe, but together, hydrogen and oxygen also form one of the most powerful rocket fuels known to humanity. This is the concept of in situ resource utilization, and it's a complete game changer. Instead of launching every single drop of water and every tank of fuel from Earth at an astronomical cost, future missions could use asteroids as cosmic gas stations. A deep space mission could dock with a water-rich asteroid, extract the ice, and process it into the fuel needed to journey even farther. This turns the entire solar system from a forbidding void into a connected highway with rest stops along the way. The theory became undeniable reality with the stunning findings from NASA's osiris-rex mission at the asteroid Bennu. When the spacecraft arrived, it didn't find the smooth, sandy surface many scientists had predicted. Instead, it was greeted by a world of astonishing roughness, littered with boulders, but its instruments peered deeper, analyzing the composition of the surface material. The data sent back was unequivocal. Bennu is rich in clay minerals that can only form in the presence of substantial amounts of water. This asteroid, a battered relic from the solar system's birth, is a water-bearing body, its geology forever altered by the liquid that once flowed through its parent asteroid long before it was shattered into fragments. This single mission provided the tangible, on-the-ground evidence that confirmed what the telescopes had hinted at, turning a scientific hypothesis into a concrete fact and opening our eyes to the incredible, resource-rich nature of these nomadic worlds. And just when you thought the idea of water on these space rocks was paradigm-shifting, our countdown brings us to number 24, a discovery that ventures from the realm of geology into the very origins of life itself, the presence of complex organic molecules. We're not talking about simple carbon compounds. We're discussing a rich inventory of carbon-based building blocks, the same essential ingredients that, under the right conditions, can assemble into the complex structures of living organisms. For years, the notion that such delicate, life-related chemistry could survive the harsh environment of space seemed far-fetched, yet the evidence is now undeniable, thanks in large part to a technological triumph of modern exploration, Japan's Hayabusa 2 mission to the asteroid Ryugu. This wasn't just a flyby. It was a precision operation that involved touching down on the asteroid's surface, collecting precious material, and sealing it inside a capsule for a fiery return journey to Earth. When scientists in pristine, clean rooms finally cracked open that container, they weren't just holding ancient rock. They were holding a time capsule from the dawn of the solar system, and its contents were breathtaking. Analysis revealed a veritable soup of organic matter, including amino acids, the very molecules that string together to form proteins, which are the workhorses of every single cell in your body. Finding them on an asteroid, millions of miles from Earth, is like finding a fully stocked kitchen, complete with all the raw ingredients, adrift in the middle of the ocean. This discovery fuels one of the most profound and debated theories in all of science, panspermia. The word itself comes from Greek roots meaning seeds everywhere, and the theory proposes that the fundamental components for life are not unique to Earth, but are instead scattered widely across the cosmos, hitchhiking on asteroids, comets, and dust grains. The finding of amino acids on Ryugu provides the strongest support yet for this idea. It suggests that the early Earth, a newly formed and still cooling planet, was likely seeded with these organic compounds through a relentless bombardment by asteroids just like it. Instead of life's chemistry having to start from absolute scratch in some primordial pond, the pond may have been pre-seasoned with a rich broth delivered from the heavens. This doesn't mean we've found evidence of ancient alien life on an asteroid. What we've found is arguably more fundamental. We've found the potential for life, the universal Lego bricks that, given a stable and nurturing environment like the early Earth, could have eventually clicked together to form the first self-replicating systems. It transforms our perspective from one of earthly isolation to one of cosmic connection, hinting that the processes that led to us are not a bizarre fluke, but might be a natural, and perhaps common, outcome of cosmic evolution. Think about the sheer resilience this implies. These organic molecules endured for over 4.5 billion years. They survived the violent breakup of Ryugu's parent body, the relentless radiation from the sun, and the extreme temperatures of deep space. Their survival tells us that the chemistry of life is incredibly robust, capable of weathering the most unforgiving environments the universe can throw at it. This has staggering implications for the search for life beyond Earth. If asteroids like Ryugu can act as cosmic delivery trucks, then any planetary system with similar asteroids could have received the same generous endowment. Moons like Europa or Enceladus, with their subsurface oceans, might have had their waters enriched by these organic deliveries long ago. The discovery on Ryugu doesn't just tell a story about our own past, it paints a picture of a galaxy that could be teeming with the raw materials for biology, waiting only for a suitable world to call home. We are left with a humbling and exhilarating thought. The elements that make up our bodies were forged in the hearts of long-dead stars, and the basic blueprints for life itself may have been written in the dark, cold void between them, carried across the immense distances on silent, rocky vessels like Ryugu. Moving from the chemical building blocks of life to the hidden forces that once shaped these worlds, we arrive at number 23 on our list, the ghostly presence of ancient magnetic fields. This is a discovery that sounds almost like science fiction, the idea that a seemingly inert, cold rock drifting through space could still be holding onto a faint, fossilized echo of a magnetic field from billions of years ago. Unlike the powerful, global magnetic field generated by Earth's churning molten core, what scientists are finding on some asteroids are remnant magnetizations, literally frozen into the very rock itself. It's a pale shadow of a once great force, a cosmic memory locked in stone. Detecting something so subtle on a body millions of miles away is a monumental feat of scientific ingenuity. It's not done with a simple magnetometer sweep from orbit. Instead, researchers analyze meteorites that have fallen to Earth, which are known to be fragments of specific asteroid types. In sophisticated labs, they subject these samples to intense scrutiny, looking at tiny magnetic minerals within the rock. These minerals, like miniature compasses, align themselves with the magnetic field that was present when the rock last cooled from a molten state. By measuring the direction and strength of this locked-in magnetization, scientists can effectively read the history book, determining the strength and even the nature of the magnetic field that existed when that asteroid, or more accurately, its parent body, was young. The implications of this discovery are profound, completely reshaping our understanding of asteroids. A magnetic field isn't something a small, simple pile of rubble can generate on its own. For a world to have a global magnetic field, it needs a dynamo, a swirling, molten, electrically conductive core, like the one inside Earth. The undeniable presence of this fossil magnetism on asteroid fragments is therefore incredibly strong evidence that these asteroids are not the primordial building blocks they were once thought to be. Instead, they are the shattered remains of something much, much grander. They are the wreckage of fully formed, differentiated protoplanets that existed in the early solar system. Differentiation is a key planetary process where a body gets hot enough, often from the heat of radioactive elements, to melt internally. In this molten state, heavy materials like iron and nickel sink to the center to form a metallic core, while lighter silicate minerals float to the surface to form a crust. It's during this violent, formative period that a molten metal core can churn and generate a powerful magnetic field. The asteroid we see today, then, is just a piece of the crust or mantle from one of these lost worlds, a world that was subsequently shattered in a colossal collision. The magnetic signature is a ghost from that world's vibrant, molten heart. This dramatically alters the narrative of our solar system's infancy. The early days weren't a peaceful gathering of dust. They were a chaotic and violent construction zone, with dozens, perhaps even hundreds, of these Mars-sized or larger protoplanets forming and evolving. They weren't just simple rocks. They were complex, layered worlds with their own geology, their own molten cores, and their own protective magnetic shields. This period was a celestial demolition derby, and the asteroid belt we see today is the ultimate graveyard, the leftover debris from that epic era of planetary carnage. Every time we find a magnetized meteorite or detect a hint of a remnant field, we are collecting a piece of evidence from a crime scene that is 4.5 billion years old. We are holding a piece of a planet that never was, a world that had the potential to grow, but was tragically annihilated in the turbulent dynamics of the young solar system. This discovery connects the dots in our own planet's history as well. Earth itself is one of the lucky survivors of that brutal era, having grown by accreting countless such fragments, perhaps even incorporating pieces of these very same destroyed protoplanets into its own structure. The iron in your blood may have once been part of the core of a world that no longer exists, and now we reach a concept that fundamentally challenges our very idea of what an asteroid is. At number 22 on our list, we encounter the bizarre and counterintuitive reality of the rubble pile asteroid. For centuries, the mental image was simple: a single, solid chunk of rock or metal hurtling through space. But modern science has completely shattered that illusion. We now understand that a significant number of asteroids, perhaps even the majority of the larger ones, are not monoliths at all. They are exactly what the name implies: loose, unconsolidated collections of boulders, gravel, and dust, all gently held together by their own exceedingly weak gravity. Imagine a gigantic, cosmic sandcastle, or a pile of rubble left behind after a demolition, slowly spinning in the void of space. That is the true nature of many of these objects. The first major clues came from a seemingly simple measurement: density. Astronomers can calculate an asteroid's mass by observing its gravitational influence on passing spacecraft or other asteroids. They can also estimate its volume by carefully measuring its size. When you divide the mass by the volume, you get its overall density. For many asteroids, the results made no sense if they were solid rock. The calculated densities were astonishingly low, often less than the density of water, meaning these asteroids would theoretically float if you could find an ocean large enough to put them in. A solid object made of stone should be 2 to 3 times denser. The only logical explanation was that these asteroids are mostly empty space. They are porous aggregates with countless gaps and voids between the constituent pieces. The final, undeniable proof came from close-up visits. When the Japanese Hayabusa spacecraft arrived at the asteroid Itokawa, it beamed back images of a world that looked like a handful of gravel had been haphazardly clumped together. Itokawa was covered in boulders of all sizes, with no clear, solid surface, appearing fragile enough that you might be able to kick it apart with your foot. This was not a single rock, it was a collection, a floating construction site of primordial debris. This understanding transforms a theoretical concept into a matter of planetary defense with immense practical consequences. The rubble pile structure makes predicting an asteroid's behavior incredibly difficult. If we were to attempt to deflect a threatening solid asteroid, a well-planned nuclear detonation, or a kinetic impactor, essentially slamming a heavy spacecraft into it, could, in theory, give it a predictable nudge, altering its course enough to miss Earth. But a rubble pile is a different beast entirely. A powerful impact on such an object doesn't necessarily push the entire asteroid. Instead, the energy is absorbed by the countless gaps and spaces, dissipating through the pile in unpredictable ways. It could simply reshape the asteroid, or worse, shatter it into a cloud of smaller but still dangerous fragments, turning a single bullet into a shotgun blast aimed directly at our planet. This realization has forced a complete rethink of asteroid deflection strategies. Scientists are now exploring more gentle, gradual methods, like using a gravity tractor, a spacecraft that would fly alongside the asteroid for years, using its own tiny gravitational pull to slowly and gently tow the rubble pile onto a safer path, ensuring it stays in one piece. This fragile nature also provides a fascinating window into the violent history of the asteroid belt itself. A rubble pile is essentially the aftermath of a cosmic collision. It is the reassembled debris from a once larger parent body that was utterly shattered by a catastrophic impact. The fact that so many asteroids have this structure tells us that the process of smash-up and gravitational reaccumulation is not just common. It's the dominant geological process in the asteroid belt. These objects are not pristine relics. They are the phoenixes of the solar system, constantly being born from the ashes of their predecessors. Their very existence is a testament to the relentless cycle of destruction and rebirth that has shaped our cosmic neighborhood for billions of years, with each pile holding the fossilized record of the immense forces that created it. As we venture into the most unexpected findings on our list, we arrive at number 21, a discovery that feels like something out of a cosmic treasure hunter's wildest dream: the existence of asteroids with surfaces almost entirely made of metal. This isn't just a slight enrichment of iron. We're talking about worlds that appear to be predominantly composed of iron and nickel, shining with a dull, metallic gleam in the distant sunlight. The most famous example, and the one that has captured the imagination of scientists and the public alike, is an asteroid named 16 Psyche. Located in the main asteroid belt, Psyche is a colossal object, about 226 kilometers across. For decades, astronomers have known it was unusual. Measurements of the light it reflects, its density, and its thermal properties all pointed to a composition radically different from the stony or carbon-rich asteroids we've discussed so far. The data screamed one thing: this isn't a rock, it's a massive, metallic world. The leading theory to explain such a bizarre object is as dramatic as it is compelling. Scientists believe that Psyche, and others like it, are the shattered, exposed cores of early protoplanets. Remember the story told by the fossil magnetic fields of differentiated worlds with molten metal cores. Psyche is thought to be the ultimate evidence of that process, a surviving relic of that violent period. The theory goes that in the solar system's youth, a fully formed, layered protoplanet, complete with a silicate mantle and a molten iron-nickel core, was involved in a series of catastrophic collisions. These impacts were so violent that they systematically and utterly blasted away the entire rocky mantle, leaving behind only the dense, metallic heart of the planet, which we now see as the asteroid Psyche. If this theory is correct, then we have never before been able to study a planetary core directly. Every piece of data we have about the cores of Earth, Mars, or Venus comes indirectly from seismic waves or magnetic field measurements. Psyche offers a once-in-a-lifetime opportunity to stare directly into the fiery, metallic engine that powers a planet's magnetic field and drives its geology. Just imagine the vista from the surface of such a world. The landscape would be utterly alien, a jagged terrain forged in extreme heat and pressure. Instead of the familiar gray dust of the moon, the ground would be a dark, rust-colored metallic expanse, strewn with strange, eroded features. You might see towering metal cliffs, sharp ridges, and vast, smooth plains where molten metal once flowed and solidified. There could be enormous, otherworldly craters, but unlike the bowl-shaped impressions on rocky bodies, impacts on a metallic surface might create bizarre, splattered formations or leave behind strange, magnetic debris. The gravity, while weak, would feel different, more substantial due to the incredible density of the material beneath your feet. The entire environment would be dominated by the presence of metal in a way that exists nowhere else in our solar system, a monument to both creation and destruction on a planetary scale. This brings us to the tantalizing prospect that makes metal-rich asteroids a topic of intense discussion beyond just scientific circles: the potential for asteroid mining. The sheer amount of raw material present in an object like Psyche is difficult to comprehend. Preliminary estimates suggest it contains enough iron and nickel to supply our global metal needs for millions of years at current consumption rates. But the value goes far beyond common industrial metals. Within this metallic mix, scientists anticipate finding incredibly rare and precious metals like platinum, gold, cobalt, and iridium in concentrations that are orders of magnitude higher than the minuscule traces we painstakingly mine from Earth's crust. A single, relatively small metallic asteroid could contain more platinum than has ever been mined in all of human history. The economic implications of being able to access such a reservoir are, quite literally, astronomical, potentially creating the first trillion-dollar industry in space and fundamentally altering the resource base of our entire civilization. Of course, turning this vision into reality presents staggering engineering and economic challenges. The energy required to travel to the asteroid belt, extract materials in the airless, low-gravity environment, and then transport them back to Earth or to construction sites in orbit is immense. We would need to develop entirely new technologies for autonomous mining and processing in space. Yet, the potential payoff is so transformative that both government space agencies and private companies are already seriously studying the concepts. The key insight is that the most valuable application for these space mine metals may not be bringing them back to Earth, where they could crash markets, but rather using them in space itself. Imagine building enormous space stations, solar power satellites, or deep space vessels not from materials launched at tremendous cost from the bottom of Earth's gravity well, but from metal refined and manufactured just a few million miles away. This is the true promise of metal-rich asteroids. They could provide the raw materials to build a sustainable, expanding human presence throughout the inner solar system, turning them into the foundational resource for a truly spacefaring civilization. NASA's upcoming Psyche mission, set to arrive at the asteroid in 2029, will be our first close-up look at this metallic marvel, and the data it returns won't just rewrite our science textbooks. It might very well lay the groundwork for our industrial future among the stars. At number 20 on our list, we encounter a configuration that seems to defy simple logic: the binary asteroid system. Far from being lone wanderers, a surprising number of these space rocks are actually pairs, locked in a perpetual gravitational embrace as they journey together around the Sun. Picture two distinct asteroids, sometimes similar in size, other times with one much larger than the other, endlessly circling a common center of gravity between them, performing a slow, silent ballet in the void. This discovery fundamentally changed our understanding of asteroid dynamics. revealing that their interactions are far more complex and social than we ever imagined. The formation of these cosmic duos is a story of violence and physics. One of the primary mechanisms is thought to be a close encounter or a gentle collision. When a larger asteroid is grazed by a smaller one at just the right speed and angle, the smaller body can be captured by the larger's gravity, settling into a stable orbit rather than crashing into it or flying off into space. Another fascinating method is through a process called rotational fission. Imagine a single, loose, rubble pile asteroid spinning faster and faster, perhaps because it's being pushed by the subtle but constant pressure of sunlight, a phenomenon known as the Yarkovsky-O'Keefe-Radzievsky-Paddock, or YORP, effect. As its rotation accelerates, the centrifugal force at its equator can eventually overcome its meager gravity, causing it to literally fling material off into space. This ejected material doesn't always escape entirely. Instead, it can coalesce into a smaller, secondary asteroid that begins to orbit the primary, creating a brand new binary system from what was once a single, spinning object. Perhaps the most famous and impactful example of a binary system is Didymos and its tiny moon, Dimorphos. Didymos, the larger primary asteroid, is about 780 meters across, while Dimorphos is a mere 160 meters in diameter, roughly the size of the Great Pyramid of Giza. This pair became household names because they were the target of humanity's first ever planetary defense test, NAS, a double asteroid redirection test, or DART mission. The genius of choosing a binary system for this historic experiment was that it provided a perfect, natural laboratory. By crashing the DART spacecraft into the smaller moonlet, Dimorphos, scientists could precisely measure the change in its orbit around Didymos. They didn't have to measure a tiny shift in the entire system's path around the Sun. They simply had to clock how much faster the little moon completed its orbit after the impact. The success of DART proved that we could, in principle, nudge a threatening asteroid off course, and it was only possible because of the unique orbital dynamics of a binary pair. Watching a simulation of these systems is like observing a masterclass in celestial mechanics. Their orbits can be remarkably fast. Dimorphos, for instance, originally orbited Didymos about once every 12 hours. The dances they perform are not always simple circles. Some have highly elliptical paths, bringing the secondary asteroid swooping in close before swinging it far out again. In even more complex configurations, there are triple asteroid systems, where two moons orbit a primary body, creating a miniature solar system in its own right. The sheer variety of these systems tells us that the processes of collision, capture, and rotational disruption are not rare events, but common and ongoing parts of the asteroid belt's evolution. Each binary pair is a frozen record of a specific moment of transformation, a snapshot of the forces that continue to sculpt our solar system billions of years after its formation. But just when you think you've got asteroids neatly categorized as inert rocks or metallic cores, the universe throws another curveball. At number 19 on our list, we encounter one of the most visually stunning and scientifically baffling phenomena, the active asteroid, an object that blurs the very line between asteroid and comet. The classic distinction was simple. Comets are icy snowballs from the outer solar system that develop glorious, glowing tails as they approach the sun and their ices vaporize. Asteroids, on the other hand, are rocky or metallic and inert, showing no such activity. This neat division was shattered when astronomers began spotting asteroids in the main belt, the region between Mars and Jupiter, far from the sun's intense heat, sporting their own faint, comet-like tails and plumes of dust. This process, known as outgassing, is the bizarre behavior that defines these hybrid objects. Instead of a placid, unchanging surface, these asteroids are dynamically ejecting material into space, creating a transient, hazy atmosphere called a coma, and often a long, thin tail that streams away from the sun's radiation pressure. One of the most spectacular examples is an object designated 311P/Pan-STARRS. When observed by the Hubble Space Telescope, it didn't show a single typical tail. Instead, it revealed 6 separate, changing dust tails, fanning out like the spokes of a bicycle wheel. It looked less like a simple space rock and more like a celestial sprinkler, rotating and sporadically firing jets of fine material into the void. This was not the behavior of a dead relic. This was the signature of an object undergoing profound change. So what could possibly be causing a dry, rocky asteroid to suddenly start spewing dust? Scientists have several compelling theories, each pointing to a different, fascinating internal process. The leading suspect is the sudden exposure of subsurface ice. Remember the water ice we discussed earlier, thought to be buried deep within many asteroids. If a recent, even small, impact were to crack open the asteroid's protective, dusty crust, it could expose that buried ice to the vacuum of space and the faint warmth of the distant sun. Without any air pressure, solid ice doesn't melt into liquid. It instantly sublimates, turning directly from a solid into a vigorous jet of gas. This outburst of vapor then acts like a geyser, lifting and carrying fine surface dust along with it as it erupts into space, creating the visible plumes and tails we observe. Another potential trigger is the asteroid's own rotation, driven by that subtle Yarkovsky-O'Keefe-Radzievskaya-Paddock effect. As sunlight heats an asteroid's surface, the warm side radiates that heat away as infrared light, imparting a tiny amount of thrust. Over millions of years, this can cause a rubble pile asteroid to spin faster and faster. As the centrifugal forces build, they can destabilize the entire structure, causing landslides and exposing fresh, volatile, rich material from within. The asteroid essentially shakes itself apart, and the newly freed material, including any trapped ices or gases, vents into space. In the case of 311P/Pan-STARRS, its multiple, changing tails are thought to be the result of a series of such rotational breakup events, where the asteroid spun so fast it began to shed material in distinct bursts. There's also the possibility of thermal fracture. The surface of an asteroid experiences extreme temperature swings, from searing heat in direct sunlight to bitter cold in shadow. This constant thermal cycling can cause rocks to crack and shatter over time. If those rocks contain tiny pockets of trapped gas or even ices, the fracturing can release that pent-up pressure in a small, localized explosion of dust. What makes active asteroids so compelling is that they are not ancient, stable worlds. They are dynamic bodies caught in the act of transformation. We are witnessing their geology in real time, watching as internal and external forces remodel them before our very eyes. The discovery of these active objects forces a major rethink of the solar system structure and the distribution of water. Finding volatile materials like water ice on asteroids in the main belt suggests that the boundary between the inner rocky planets and the outer icy realms is far more porous than we ever believed. It implies that water was not just delivered to Earth by comets from the far edges of the solar system, but was also readily available from local asteroids that have been hiding their icy secrets just beneath the surface all along. Every time one of these asteroids activates, it's like a flashbulb going off in the dark, briefly illuminating the hidden ingredients that have been lurking there for eons. They are a powerful reminder that in the silent vacuum of space, even what appears to be a dead rock can still harbor unexpected, dynamic life. Stepping away from the dynamic tails of active asteroids, our journey into the bizarre now takes us to the very form of these cosmic nomads. At number 18, we find that their shapes are anything but ordinary, defying the simple, spherical image we might hold of planets and moons. When the first close-up images from spacecraft began to beam back, they didn't reveal perfect spheres. they unveiled a gallery of the peculiar and the misshapen. We've encountered asteroids that look like giant dog bones, spinning through the void as if tossed by some cosmic pet. We've seen worlds with the precise geometry of a cut diamond, and others that are so lumpy and elongated they resemble baked potatoes more than celestial bodies. These strange forms are not random quirks. They are the direct, unvarnished result of a life spent in the chaotic demolition derby of the asteroid belt. Each irregular contour a scar and a story. Consider the asteroid Cleopatra, for instance, a main belt object that has been vividly mapped by ground-based radar. This astonishing body is over 270 kilometers long, but only about 60 kilometers thick at its center, forming that unmistakable dog bone shape. How does such a thing even form? The leading theory suggests it is the product of a grazing, low-speed collision between two larger asteroids. Instead of shattering each other, they merged in a messy, incomplete union, creating this bizarre, bilobed structure. Its weak gravity, barely strong enough to hold the two lobes together, gives it an incredibly low density, implying it's little more than a loose pile of metallic rubble. Cleopatra is essentially a testament to a cosmic near miss, a world that came within a fraction of being completely destroyed, and instead was sculpted into one of the strangest shapes in the solar system. The reason most asteroids lack a spherical form comes down to a simple but fundamental force: gravity. For a body to pull itself into a round shape, its own gravitational force must be strong enough to overcome the material strength of the rock or ice it's made from. This is a state known as hydrostatic equilibrium, and it's a key dividing line between small, irregular asteroids and larger, spherical dwarf planets. Most asteroids are simply too small. Their gravity is so feeble that the rocks and dust they are composed of are stronger than the pull trying to compact them. They don't have the mass to crush themselves into a ball, so they retain every jagged edge, every strange concavity, and every elongated form bestowed upon them by countless collisions. This is why the transition from asteroid to dwarf planet is so significant. When we look at Ceres, the largest object in the asteroid belt, we see a world that is round, its gravity having successfully sculpted it into a sphere, marking it as a more evolved and massive body. The stories etched into these irregular shapes are dramatically amplified when we examine their surfaces up close. The data and stunning 3D models returned by missions like NAS, a Dawn spacecraft, which orbited both Vesta and Ceres, have given us an unparalleled view of this violent topography. Vesta, the second most massive body in the belt, is a world covered in geological drama. It is dominated by a colossal impact basin near its south pole, so enormous that it is named Resilvia, a crater 500 kilometers across, which is almost as wide as Vesta itself. The impact that created this scar was cataclysmic, so violent that it nearly shattered the entire protoplanet and is responsible for a whole family of smaller asteroids, known as Vestoids, that were blasted into their own orbits around the Sun. The 3D models reveal a central peak within Resilvia that towers over 20 kilometers high, making it one of the tallest mountains in the entire solar system. The entire shape of Vesta is warped by this ancient trauma, a permanent deformation caused by an event of almost unimaginable power. Then there is the presence of truly immense boulders, some of which dwarf even the largest structures on Earth. Back on the asteroid Itokawa, the Hayabusa mission found boulders that were dozens of meters wide on a body only a few hundred meters across, proportions so extreme it would be like finding a skyscraper-sized rock sitting on a small hill. On Bennu, the osiris-rex mission discovered that its surface was an obstacle course of house-sized boulders, with very few clear, sandy areas for the spacecraft to safely touch down. These aren't just random rocks, they are the surviving fragments of earlier, obliterated asteroids. pieces that were jumbled together during the gentle gravitational collapse that formed these rubble pile worlds. Their sheer size and abundance tell us that the forces involved in the collisions that build and destroy asteroids are capable of creating and tossing around building-sized chunks of primordial stone as if they were mere pebbles. The combination of these strange shapes and violent topographies forces us to completely reconsider the environment of the asteroid belt. It is not a placid, orderly ring of rocks quietly orbiting the sun. It is a chaotic and brutally active shooting gallery, where high-speed collisions are a regular and defining occurrence. Every bizarre shape, from the spinning tops to the dog bones, is a frozen snapshot of a specific impact event. Every colossal crater is a bullseye from a past catastrophe, and every gigantic boulder is a piece of shrapnel from a long-forgotten planetary battle. These asteroids are not pristine relics. They are the battered and reshaped survivors of 4.5 billion years of cosmic bombardment, their very forms serving as a living museum of the impact history that has shaped our entire solar system. Ceres, that rounded behemoth of the asteroid belt, has long been something of an enigma, a world that defied easy categorization, but the discovery we're about to explore elevates it from a mere curiosity to a place of profound geological intrigue. At number 9 on our list, we uncover one of the most bizarre findings in the entire belt: the clear and undeniable evidence of past volcanism on its surface. This isn't the kind of fiery, lava-spewing volcanism we see on Earth or Io. This is something colder, stranger, and potentially far more significant. We are talking about cryovolcanism, ice volcanoes that erupt not with molten rock, but with a chilly, briny mud, a slurry of water, salts, and rocky material. The star of this cryovolcanic show is a singular mountain named Ahuna Mons. When NASA's Dawn spacecraft mapped Ceres in exquisite detail, this feature stood out like a sore thumb alone, towering dome rising 4 kilometers high from an otherwise relatively smooth landscape. Its slopes are streaked with bright, reflective material, and its surface is remarkably free of the large craters that pockmark the rest of Ceres, suggesting it is geologically young, perhaps only a couple 100 million years old. This youth was the first major clue that Ahuna Mons wasn't formed by a typical impact. Its very existence posed a monumental question: how does a mountain this large and this fresh form on a small, cold world that was presumed to be geologically dead? The answer, pieced together from painstaking analysis, is that Ahuna Mons is a cryovolcano. It is a vast mound of material that oozed up from Ceres's deep interior and piled up on the surface, a frozen testament to a time when this dwarf planet had a restless, slushy heart. The mechanics of an ice volcano are fascinatingly alien. Instead of a chamber of molten rock, a cryovolcano is fed by a reservoir of liquid or semi-liquid water, thick with dissolved salts and clays, known as a cryomagma chamber. The antifreeze that keeps this water liquid in the deep cold of space is the salt content. Just as we salt our roads to melt ice in winter, high concentrations of salts, like sodium carbonate, dramatically lower the freezing point of water. Deep beneath the surface, insulated by overlying rock and ice, this briny slurry remains liquid. Then, some trigger, perhaps a build-up of pressure from gases, or a fracture caused by a large impact, forces this cold, muddy mixture upward. It doesn't explode violently like Mount St. Helens. It more likely extrudes, flowing slowly upward and outward like thick toothpaste, freezing solid in the vacuum of space and building the distinctive dome shape of Ahuna Mons over time. The implications of an active cryovolcano on Ceres are nothing short of revolutionary for our understanding of the asteroid belt. For a world to have any kind of volcanism, it needs an internal heat source. A small, cold rock shouldn't have one. So where did Ceres get the energy to power its icy eruptions? The leading theory points to the decay of radioactive elements within its core, the same process that heats Earth's interior. But for a body as small as Ceres to have retained enough heat for so long, and for that heat to be sufficient to maintain pockets of liquid water, suggests its interior is far more complex and dynamic than anyone ever dreamed. It implies that Ceres is a differentiated world with a rocky core, a thick mantle of water ice, and possibly a deep, residual layer of liquid brine sandwiched in between. This isn't just a frozen fossil, it's a world that has been geologically alive for a significant portion of the solar system's history, with its own internal engine quietly driving change on the surface. This discovery immediately and powerfully shifts the conversation about Ceres toward one of the most exciting topics in modern science: potential habitability. Where there is persistent liquid water, there is at least the possibility of environments where life could gain a foothold. The briny fluids that erupted from Ahuna Mons didn't just contain water. They were rich in organic compounds and essential minerals. This mixture of liquid water, organic material, and a long-lasting heat source checks several of the most critical boxes required for life as we know it. While we are not saying life exists on Ceres, we are stating unequivocally that it possesses the key ingredients. The eruptions themselves may have even served to transport these life-friendly materials from the warm, dark depths to the surface, creating transient, accessible niches where chemistry could have become increasingly complex. The story of Ceres' volcanism becomes even richer when we look beyond Ahuna Mons. Detailed geological mapping has revealed the ghostly outlines of other, much older cryovolcanos across the surface. These ancient structures have been so battered and smoothed by billions of years of impacts that they are now little more than subtle, wide domes, recognizable only by their distinctive shape and the composition of their material. This tells us that cryovolcanism on Ceres wasn't a one-time fluke with Ahuna Mons. It has likely been an ongoing, intermittent process for ages. The internal heat that drives it ebbs and flows, occasionally finding a weak spot in the crust to breach, reminding us that even in the apparent stillness of the asteroid belt, worlds can have active, albeit slow motion, geological lives. This transforms Ceres from a simple, large asteroid into a prime candidate for future exploration, a place where we might one day search not for life itself, but for the answers to whether the conditions for life are a common gift throughout our solar system. But our exploration of the bizarre doesn't end at the boundaries of our own solar system. At number 10, we must venture beyond to consider perhaps the most enigmatic visitor ever observed, the interstellar object known as Oumuamua. In 2017, a telescope in Hawaii scanning for near-Earth asteroids detected a faint point of light moving at a speed so blistering, its trajectory could only mean one thing: it was not from here. This was our first confirmed guest from another star system, a cosmic tourist just passing through, and its brief appearance ignited one of the most intense and fascinating scientific debates of the modern era. The first major anomaly was its shape, based on the dramatic way its brightness changed as it tumbled through space. Astronomers calculated that Oumuamua was highly elongated, shaped less like a potato and more like a pancake or a cigar, with estimates suggesting it was up to 10 times longer than it was wide. While some asteroids in our own system are elongated, nothing we've seen comes close to these extreme proportions. This was no simple, lumpy rock. It was a shape that seemed almost engineered, defying our expectations of how natural objects form through collisions and accretion. Then came the second, and even more perplexing, mystery: its motion. As Oumuamua sped away from the sun, scientists tracking its path noticed something inexplicable. After accounting for the gravitational pull of the sun and all the planets, it was still accelerating, just a tiny bit, but enough to be detected. This is known as non-gravitational acceleration, and while comets often exhibit this when their ices heat up and create jet-like outgassing, Oumuamua displayed no visible coma, no tail, no cloud of gas or dust around it whatsoever. It was acting like a comet, but looking like a sterile, rocky asteroid. The absence of a clear, natural explanation is what opened the door to some truly wild theories. The most famous, proposed by Harvard astronomer Avi Loeb, was the possibility that Oumuamua could be a piece of alien technology, specifically a light sail. A light sail is a proposed method of spacecraft propulsion that uses the gentle but constant pressure of sunlight against a vast, thin membrane to build up speed, much like a boat's sail catches the wind. This could neatly explain the non-gravitational acceleration. As the object moved away from the sun, the radiation pressure was giving it an extra push. Loeb suggested that Oumuamua's unusual flatness and brightness could be consistent with a discarded light sail, a piece of a long derelict extraterrestrial probe drifting through the galaxy. While this idea was met with immense skepticism from the broader scientific community, it captured the public imagination and forced a crucial conversation about how we interpret data when faced with the truly unknown. The more mainstream scientific consensus gradually coalesced around a more natural, yet still fascinating, explanation. The leading theory now posits that Oumuamua is likely a fragment of a Pluto-like world from another solar system, a chunk of solid nitrogen ice that was shorn off its parent body by a colossal impact. This theory elegantly solves several puzzles at once. First, a slab of nitrogen ice would have the necessary strength to maintain such an extreme, flattened shape without fracturing. Second, as it approached our sun and heated up, the nitrogen ice would have sublimated directly from a solid to a gas, providing the thrust for the observed acceleration. And crucially, nitrogen gas is very difficult to detect with telescope. It doesn't glow or create a visible dusty tail like water ice does. So Oumuamua was outgassing like a comet, but it was doing so with a stealthy propellant that left no obvious trace for our instruments to see. Other theories suggest it could be a loose aggregate of dust particles, a sort of dust bunny on an interstellar scale, whose extremely low density would allow light pressure to affect its motion significantly. Regardless of its ultimate identity, Oumuamua's fleeting visit was a watershed moment for astronomy. It taught us that interstellar objects are likely far more common than we ever thought, with some estimates suggesting there could be thousands within our solar system at any given time, previously too faint and fast for us to notice. Its bizarre properties revealed a diversity of planetary systems and formation processes that we are only beginning to comprehend. Before Oumuamua, our models of planet formation were based solely on our own solar system. Now, we have direct evidence that other star systems can eject material that is profoundly different from anything we have here, from exotic ices to objects with shapes we never imagined. It was a tantalizing, if frustratingly brief, glimpse into the vast and varied galactic inventory, a single data point that forever changed our perspective from a solar system-centric view to a galactic one, reminding us that the cosmos is far stranger and more wonderful than our earthly experience can prepare us for. Just when you think you've grasped the nature of these solitary space rocks, the universe presents yet another layer of complexity. At number 11 on our list of bizarre asteroid discoveries, we find a configuration that once seemed almost impossible: asteroids that have moons of their own. For a long time, the very idea was dismissed. How could an object with such a minuscule gravitational pull possibly capture and hold a satellite in orbit? Yet, the evidence is now undeniable, and it turns out this is not a rare cosmic fluke, but a surprisingly common arrangement throughout the asteroid belt. These aren't just lone wanderers. many are miniature planetary systems, complete with their own tiny, orbiting companions, turning the simple asteroid into the center of its own gravitational family. The first confirmed discovery of an asteroid moon sent shockwaves through the astronomical community and forever changed our textbooks. This historic moment came in 1993 when NASA Galileo spacecraft, on its way to Jupiter, flew past the asteroid 243 Ida. As the probe sent back images of this 52-kilometer-long cratered world, scientists noticed a tiny speck of light hovering nearby. Further analysis confirmed the incredible: Ida had a companion. This small moon, later named Dactyl, is only about 1.5 kilometers across, a tiny pebble orbiting a slightly larger rock. The existence of Dactyl proved conclusively that asteroids could indeed possess moons, forcing a complete re-evaluation of their dynamics and formation history. Since that landmark discovery, hundreds of other binary and even triple asteroid systems have been identified, showing us that these cosmic partnerships are a fundamental part of the asteroid belt's architecture. So how does a small, rocky body with barely any gravity manage to acquire a moon? The processes are as fascinating as they are violent. One of the primary methods is through impact ejection. Imagine a larger asteroid being struck by a smaller one in a colossal collision. The impact doesn't just create a crater, it blasts a tremendous amount of debris into the space around the asteroid. While most of this material escapes entirely or falls back to the surface, some of it can be thrown into orbit at just the right speed. If the ejected debris is moving slower than the asteroid's escape velocity, it can't break free, but it's also moving too fast to fall back down. This material then begins to coalesce under its own weak gravity, eventually forming a small, secondary moon from the rubble of the ancient impact. This is likely the origin story for Dactyl and many other similar moons. Another fascinating formation mechanism ties back to the bizarre nature of rubble pile asteroids and the subtle power of sunlight. As we've discussed, the Yorp effect can cause a loose, aggregated asteroid to spin faster and faster over millions of years. When its rotation rate becomes so extreme that the centrifugal force at its equator overcomes its feeble gravity, the asteroid can literally begin to unravel. Material from its surface is flung off into space, but instead of just drifting away, this cloud of dust, gravel, and boulders can find itself in a stable orbit around the primary body. Over time, this orbiting debris can gently coalesce, pulled together by its own mutual gravity, to form a new moon. This process, known as rotational fission, essentially allows an asteroid to give birth to its own satellite simply by spinning itself apart. The presence of these moons creates a tremendous challenge for one of humanity's most ambitious space endeavors. Landing on an asteroid, navigating near a binary system, is an immensely complex task for a spacecraft. The gravitational environment is no longer simple. It's a dynamic and chaotic three-body problem. The spacecraft isn't just being pulled by the primary asteroid, it's also being subtly tugged by the moon's gravity, creating unstable zones and potential trajectory hazards that are incredibly difficult to model and predict. For a mission like osiris-rex, which targeted the single asteroid Bennu, the navigation team could focus on mapping boulders and finding a safe touchdown site. But if Bennu had a moon, the entire approach would have been exponentially more difficult, requiring constant course corrections to account for the moon's gravitational influence and its position in the sky. This complexity was starkly illustrated by NAS, a DART mission, which, as we mentioned, targeted the binary system of Didymos and Dimorphos. Just getting the spacecraft to the correct small moon, Dimorphos, and impacting it precisely was a monumental feat of navigation. The team had to account for the gravitational pull of both bodies and ensure their spacecraft wasn't deflected off course at the last second. Furthermore, the presence of a moon can create a dangerous debris environment. An orbiting moon, especially one formed from loose rubble, can continually shed small particles and dust, creating a halo of micrometeoroids that could pose a significant impact risk to any approaching spacecraft. This means that before a probe can even think about landing, it might need to carefully map this debris field to find a safe approach corridor, turning a straightforward mission into a high-stakes orbital dance. Beyond the practical challenges, these asteroid moon systems serve as perfect natural laboratories for understanding fundamental physics. Because we can precisely measure the orbits of these moons, we can calculate the mass of the primary asteroid with incredible accuracy. By combining this mass with volume measurements from images, we derive the asteroid's density, which, as we've seen, is a crucial clue to its internal composition and structure. A low density tells us it's a porous rubble pile. A high density points to a more solid, metallic body. The moon, therefore, acts as a celestial scale, allowing us to weigh an asteroid from millions of miles away. The study of these systems gives us profound insights into the collision history and evolution of the solar system, as each binary pair is a fossilized record of a specific impact or rotational event that occurred billions of years ago. These tiny companions are more than just curiosities. They are the keys that unlock the secrets of their parents' past. At number 12, we encounter a mystery locked in the very light reflecting off these distant worlds, a puzzle that requires scientists to become cosmic detectives. This is the realm of spectral mysteries, where the key to understanding an asteroid's composition isn't found by touching it, but by dissecting the faint glow it emits. Using a technique called spectroscopy, astronomers split the sunlight bouncing off an asteroid into a rainbow of colors, known as a spectrum. Within this spectrum are specific dark lines and bright bands, a unique fingerprint created as certain minerals on the surface absorb or emit specific wavelengths of light. For decades, researchers have built a vast library of these spectral fingerprints by analyzing rocks here on Earth, assuming they could match what they saw in the sky to what they knew on the ground. But a persistent and baffling problem emerged. Many asteroids display spectral signatures that are completely alien, with features that don't correspond to any known mineral in our terrestrial catalog. It's as if you had a key, but none of the locks in the entire city would accept it, forcing the realization that the chemistry of the asteroid belt is far more exotic and diverse than our limited earthly experience could have predicted. These spectral oddities point to materials and geological processes that simply don't occur naturally on our planet. One of the most significant examples involves a class of asteroids that show a pronounced and mysterious absorption feature around a wavelength of 0.7 micrometers. This signature is a telltale sign of what scientists call hydrated minerals, but not in the way we might think. It doesn't mean there are pools of water. Instead, it indicates that water molecules have become chemically bound into the crystal structure of the rocks themselves, creating minerals like clays and phyllosilicates. The mystery deepens because these minerals can only form in the presence of liquid water over extended periods. Finding their spectral signature on asteroids, which are now frozen and airless, is a direct and powerful clue that these bodies, or their much larger parent bodies, were once warm and wet enough to support aqueous alteration. This forces us to envision a time when some asteroids weren't just cold, dead rocks, but were actively heated from within, possibly by radioactive decay, creating subsurface hydrothermal systems where warm water percolated through the rock, fundamentally changing its chemistry billions of years ago. Perhaps the most profound key to unlocking the solar system's origins has come not from looking at asteroids from afar, but from studying the pieces of them that have fallen to Earth, meteorites. And within the most primitive of these space rocks, we find one of the most fundamental and ancient building blocks of all, chondrules, These are tiny, millimeter-sized spherical grains, little more than specks to the naked eye, but each one is a time capsule from the very dawn of our planetary system. Under a microscope, they are stunningly beautiful, often resembling tiny, frozen dewdrops or miniature pearls locked in stone. Their formation story is a window into the most chaotic and energetic chapter of the solar system's life. Chondrules began their existence as free-floating dust in the primordial solar nebula, a vast cloud of gas and dust that surrounded our infant sun. Then, in a flash, something happened that heated these dust grains so intensely and so rapidly that they melted completely, turning into droplets of molten rock. The central mystery that has captivated scientists for generations is the nature of that something. What could possibly produce such sudden, intense, and widespread heating in the early solar system? The leading theories each paint a dramatic picture of a violent and dynamic nursery for planets. One compelling idea points to massive shockwaves rippling through the protoplanetary disk. These shockwaves could have been generated by the gravitational turbulence of material collapsing to form the sun, or by the gravitational kicks from newly forming giant planets like Jupiter. As these waves compressed the dust-rich gas, the pressure would have spiked dramatically, heating the dust particles in an instant to temperatures well over 1,000 degrees Celsius, enough to melt rock into droplets. Another fascinating hypothesis involves immense lightning bolts, on a scale we can scarcely imagine, arcing through the dusty nebula. In this dense, dusty environment, static electricity could have built up to phenomenal levels, eventually discharging in colossal bolts that flash-heated the surrounding dust into a shower of molten rain. A third possibility invokes outbursts from the young sun itself. In its infancy, our sun was a highly active T-Tauri star, prone to gigantic flares and eruptions that would have flooded the inner solar system with intense radiation, bathing the dust and melting it where it floated. Regardless of the precise trigger, what happened next was just as critical. After their brief, fiery birth, these molten droplets did not remain liquid for long. Drifting in the cold vacuum of space, they cooled and solidified within a matter of hours or days, freezing their original composition from that specific moment in time. Then, gently, over millions of years, the force of gravity began to draw them together. These countless chondrules, along with flecks of metal and older dust, slowly accreted, piling up to form the very first planetesimals, the embryonic building blocks of planets. The meteorites that contain them, known as chondrites, are essentially the leftover construction materials that never made it into a full-sized planet. They are the unsorted rubble from the construction site of the solar system, and chondrules are the most abundant component in that rubble. Studying these tiny spheres is like reading the diary of the solar system's first few million years. Their chemical composition is a direct snapshot of the conditions in that primordial dust cloud. By analyzing them, scientists know that the early solar system was a surprisingly well-mixed place, with materials from different stellar sources blended together. The rapid cooling they experienced is recorded in their crystalline structure, telling us about the thermal environment of the nebula immediately after the heating event ceased. Because they are so ancient and have been preserved so pristinely inside their meteorite hosts, chondrules provide a baseline, a reference point against which all other geological processes in the solar system can be measured. Every planet, including Earth, was built from materials just like this, but our world's violent geological history of volcanism and plate tectonics has erased all traces of its original chondrules. To find them, we must look to the asteroids, the celestial time capsules that have held these tiny, molten messengers safe for 4.5 billion years, waiting for us to learn how to read their story. Yet amid the chaotic violence of asteroid collisions, we sometimes find pockets of an almost serene order. At number 13 on our list, we encounter a finding that reveals an unexpectedly tranquil side to these tumbling worlds, the strange case of the Itokawa sand mass. When Japan's Hayabusa spacecraft finally reached its target after a long and troubled journey, it beamed back images that astonished geologists. They didn't see a solid, rugged landscape, but something far more peculiar. The asteroid Itokawa, a mere 500 meters long, looked like a pile of gravel dumped in space, but the real surprise was the presence of smooth, flat areas that stood out starkly against the jumbled boulders. These weren't solid bedrock. They were vast, seamless patches of fine-grained sand and dust, looking for all the world like miniature deserts adrift in the void. This was the first time anyone had seen such a clear and stark segregation of materials on such a small body, a direct window into the bizarre and gentle forces of geology, in a realm where gravity is barely a suggestion. The existence of these sandy seas on Itokawa is a direct consequence of its rubble pile structure, but it's the incredibly weak gravity that makes the phenomenon so strange. On Earth, gravity is a powerful, uniform force that relentlessly pulls everything downward, creating familiar processes like landslides and river flow. On Itokawa, however, gravity is more than 1 million times weaker than what we experience. At this scale, it's no longer the dominant force. It becomes just one player among several, and often not the strongest one. In this microgravity environment, other, more subtle forces we barely notice on Earth begin to rule the day. The most important of these is simple vibration. Even a tiny impact from a micrometeorite, no larger than a grain of sand itself, can send shockwaves through the entire loosely bound structure of the asteroid. These vibrations are so weak they would be undetectable to a human standing on the surface, but in this delicate environment, they are enough to make individual particles move and shift. This process, known as granular convection or the Brazil nut effect, is the key to understanding Itokawa's sandy patches. You can see a version of this in a can of mixed nuts. When you shake it, the larger Brazil nuts tend to rise to the top, while the smaller nuts and crumbs settle to the bottom. On Itokawa, the entire asteroid is constantly being shaken by these tiny impacts and thermal stresses as it rotates in and out of sunlight. When this happens, the finer sand and dust particles slowly sift their way downward, filtering through the gaps between the larger boulders and rocks. Over millions of years, this relentless, gentle sorting has allowed the finest material to drain away from the higher, boulder-strewn areas and pool together in the gravitational lows, the most stable areas on the asteroid's irregular shape. These dust-filled hollows became the smooth, pond-like features we see today, not carved by wind or water, but patiently assembled by vibration and an imperceptibly soft gravitational pull. The discovery of these dust ponds forced a major revision of what we thought was possible on small asteroids. Prior to Hayabusa, the prevailing assumption was that the constant bombardment by micrometeorites and the solar wind would blast any fine dust off an asteroid's surface, leaving behind only a coarse, rocky terrain. Itokawa proved that some asteroids can indeed hold onto their finest particles, but they do so in a very specific way. The dust isn't evenly distributed. It's collected and protected in these specific reservoirs. This realization has profound implications for future missions that plan to land on or sample asteroids. A spacecraft trying to touch down on what looks like a smooth, safe plane could find itself sinking into a deep layer of ultra-fine, unpredictable dust, like stepping into a drift of super-fine snow. The Hayabusa team themselves faced this uncertainty, and their successful touchdown and sampling from one of these smooth areas was a heroic feat of precision engineering, proving that these dust seas, while strange, could be navigated. Itokawa's sand masses are more than just a geological oddity. They are a perfect natural laboratory for studying fundamental physics. They demonstrate how granular materials behave in an environment almost entirely free of gravitational compression. The processes that form them are so slow and gentle that they have preserved a record of the asteroid's entire history of bombardment and shaking. By studying the distribution and depth of this dust, scientists can work backwards to understand the frequency of micrometeorite impacts and the internal structure of the rubble pile itself. This tiny, grain-sized world offers a timeless lesson that even in the apparent chaos of the asteroid belt, there is a place for order and sorting, a quiet, patient geology that works not with the roaring power of volcanoes or the flow of water, but with the silent, persistent ticking of vibration and the faintest whisper of gravity. And from the gentle sorting of dust on tiny worlds, we arrive at number 14, a discovery that literally fell from the sky, offering a gift of unparalleled scientific value. This is the story of the Tagish Lake meteorite, a celestial visitor that plunged into the frozen winter landscape of a Canadian lake in 2000, and which has since been recognized as one of the most pristine and informative space rocks ever studied. Unlike most meteorites that are found years or even centuries after their fall, often weathered and altered by Earth's environment, the Tagish Lake meteorite was recovered within days from a frozen lake bed, preserved in a state of deep freeze that captured its ancient secrets in perfect suspended animation. What makes this particular meteorite so special is its classification as a carbonaceous chondrite, specifically a rare and primitive type. These are the most chemically primitive materials in the solar system, the unprocessed building blocks that never got hot enough to melt and differentiate. They are the original recipe for a planet, unchanged for 4.5 billion years, but the Tagish Lake specimen is a standout even among this elite group. When scientists carefully analyzed its delicate, charcoal-like matrix, they found an incredibly rich and diverse suite of complex organic compounds. We are not talking about simple carbon molecules. We are talking about a veritable catalog of probiotic chemistry, including a stunning variety of amino acids, carboxylic acids, and complex hydrocarbons. It was like finding a perfectly preserved time capsule from a time before the Earth even existed, a chemical snapshot of the ingredients that were floating in the protoplanetary disk, waiting to be assembled into worlds. The pristine nature of this meteorite is what allowed for such a profound discovery. Because it was recovered so quickly and kept frozen, there was minimal contamination from Earth's own biology and environment. Every organic molecule detected within it could be confidently traced back to a cosmic origin. This gave scientists a uniquely clean window into the kinds of chemical processes that were occurring in the cold, dark clouds of interstellar space and the outer reaches of the nascent solar system. The sheer complexity and abundance of the organics found within Tagish Lake demonstrate that the universe is not just capable of producing the building blocks of life, but that it does so with remarkable efficiency, creating a rich and varied organic soup even in the most inhospitable of environments. This meteorite showed us that the chemical pathway to life's complexity may not be a difficult, narrow road, but a broad highway paved by natural chemical processes common throughout the galaxy. The implications of this are staggering for the theory of panspermia, the idea that life's ingredients are widespread in the cosmos. The Tagish Lake meteorite provides the most compelling physical evidence to date that the early Earth was likely bombarded with material just like it, delivering not only water, as we've discussed, but also a full toolkit of organic compound. Our planet, in its infancy, would have been seeded with these complex molecules, effectively preload the primordial soup with the raw materials necessary for biochemistry to eventually emerge. This doesn't answer the question of how non-living chemistry transitioned into living organisms, but it powerfully suggests that the starter kit for that transition was delivered to our doorstep from the depths of space. The discovery within this unassuming lump of frozen rock strongly implies that any planetary system forming around any star could receive a similar endowment, dramatically increasing the potential for life to arise elsewhere in the universe. The Tagish Lake meteorite is more than a rock. It is a messenger, telling us that the fundamental chemistry of life is a universal phenomenon, written in the stars and delivered by the silent, rocky couriers of the asteroid belt. At number 15, we encounter a phenomenon so unexpected it took mission scientists completely by surprise, turning a quiet asteroid into an active, dynamic world right before our eyes. This is the bizarre case of asteroid spouts, the spontaneous ejection of streams of particles from the surface, a behavior witnessed in stunning detail by the osiris-rex spacecraft at the asteroid Bennu. Before the mission arrived, the expectation was that Bennu would be a relatively inert, ancient relic, a quiet pile of rubble slowly spinning in the void. But the reality was far more dramatic. The spacecraft's cameras captured multiple instances where the asteroid appeared to be alive, firing off plumes of centimeter-sized particles into the space around it. Some of these particles would fall back to the surface under Bennu's incredibly weak gravity, while others were flung out with enough speed to achieve a temporary orbit around the asteroid, creating a transient, dusty cloud. It was a sight no one had predicted, transforming our understanding of these small bodies from static fossils into geologically active objects. The leading explanation for this bizarre activity points to a process that is both simple in principle and dramatic in its consequences: thermal fracturing. To understand this, you have to picture the brutal environment an asteroid like Bennu endures. Its day-night cycle is a relentless pendulum swing between extremes. For a period of several hours, a single spot on the surface is baked in direct, unfiltered sunlight, with temperatures soaring to over 120 degrees Celsius. Then, as the asteroid rotates, that same spot is plunged into the deep shadow of night, where temperatures plummet to nearly -70 degrees Celsius. This isn't a gentle warming and cooling. It's a violent, repeated thermal shock that happens every 4.3 hours, the length of Bennu's day. The rocks on the surface are constantly expanding and contracting, a stressful cycle that over time causes immense strain. Imagine taking a glass marble and repeatedly heating it in an oven, then plunging it into a freezer. It wouldn't take long for that marble to develop tiny stress fractures and eventually shatter. The rocks on Bennu are undergoing a similar, cosmic scale version of this process. But in the vacuum of space, the effect is even more pronounced. Without an atmosphere to distribute heat gradually, the temperature gradient isn't just between day and night. It can exist across a single rock. The side facing the sun can be scorching hot, while the shaded side remains bitterly cold, creating intense internal stresses. Eventually, these stresses overcome the rock's structural integrity, and it cracks. When this happens, the sudden release of energy can be enough to pop small fragments and dust grains right off the surface, launching them into the space above. It's as if the asteroid is shedding its own skin, piece by piece, under the relentless thermal pounding of the sun. This process is further amplified by the unique nature of Bennu as a rubble pile asteroid. The surface isn't a solid, monolithic slab of rock. It's a loosely bound collection of boulders, stones, and gravel, filled with pores and voids. This porous structure means there's no strong, cohesive matrix to hold everything firmly together against the thermal stress. Cracks can propagate more easily through this fragmented material. Furthermore, scientists theorize that within the pores and cracks of these rocks, there could be tiny, trapped pockets of water or other volatile substances, locked away since the asteroid's formation. When the thermal stress causes a crack to form, it can suddenly expose these trapped volatiles to the vacuum of space. In an instant, the solid ice would sublimate, turning directly from a solid into a gas, and that small, explosive burst of gas acts like a miniature rocket thruster, providing an extra kick that helps eject the surrounding dust and pebbles. This combination of mechanical fracturing and volatile release creates the perfect conditions for the asteroid to literally spit out its own material. The discovery of these spouting events has profound implications that extend far beyond scientific curiosity. For a mission like osiris-rex, which required navigating close to the surface and briefly touching down to collect a sample, this ongoing particle ejection presented a real and unforeseen hazard. The team had to constantly monitor the environment around Bennu to ensure their spacecraft wasn't at risk of being struck by one of these naturally ejected projectiles. It forced a reassessment of what we consider a safe operating environment around an asteroid. More broadly, this activity reveals that the surfaces of airless bodies are not stable, permanent landscapes. They are constantly being refreshed and reworked. The process of thermal fracturing acts as a natural sandblaster, breaking down boulders into finer regolith over time and gradually changing the asteroid's appearance and composition. This means that an asteroid's surface age might not reflect its actual internal age. The exterior we see is a young skin, constantly being shed and replaced, hiding the truly ancient material that lies just beneath. These gentle, persistent spouts are a powerful reminder that even in the silence of space, change is the only constant, driven by the simple, relentless rhythm of light and dark. At number 16, we confront one of the most dramatic and puzzling events in recorded history, a cataclysm from the sky that left behind a trail of devastation, but no smoking gun. This is the enduring mystery of the Tunguska event, a seismic explosion that flattened an immense swath of Siberian forest in 1908, yet, bizarrely, left no trace of an impact crater. For decades, the absence of that expected hole in the ground fueled wild speculation and theories ranging from secret weapons tests to the crash of an alien spacecraft. But the scientific consensus today points to a terrifying and powerful natural phenomenon, an asteroid airburst. Picture the scene on the morning of June 30th, 1908, in a remote and largely uninhabited region of Siberia, near the Podkemonaya Tunguska River. Eyewitnesses dozens of miles away reported a brilliant blue light, as bright as a second sun, moving across the sky. This was followed moments later by a shockwave of unimaginable force that literally knocked people off their feet, shattered windows hundreds of miles away, and generated seismic waves registered as far away as England. When scientific expeditions finally reached the epicenter years later, the scale of the destruction was staggering. 80 million trees had been flattened in a radial pattern over an area of more than 800 square miles, all pointing away from a central point. Yet, at that center, the scientists found something just as shocking as the damage itself. The trees were still standing, stripped of their branches and bark, but upright. There was no crater. It was as if a giant, invisible fist had slammed into the atmosphere directly above the forest, vaporizing everything in an instant without ever touching the ground. The key to unlocking this mystery lies in understanding the physics of an airburst. When a small asteroid, or more likely, a fragile, icy comet fragment, enters Earth's atmosphere, it is traveling at hypersonic speeds, often tens of thousands of miles per hour. This creates immense pressure and friction on the leading surface, heating it to temperatures hotter than the surface of the sun. For a sturdy, metallic asteroid, this heat and pressure might be survivable, allowing it to punch through and create a classic impact crater. But if the incoming object is a stony asteroid that is particularly porous or a brittle, icy comet nucleus, it's like throwing a snowball into a blast furnace. The object cannot withstand the phenomenal stresses. It doesn't gently break apart. It undergoes a catastrophic, explosive disintegration high in the atmosphere. transforming its immense kinetic energy, the energy of its motion, almost instantly into a devastating blast of heat and pressure. This is an airburst, a massive explosion occurring not on the ground, but in the sky. The estimated size of the Tunguska object underscores just how powerful this process can be. Scientists calculate it was relatively small, probably only about 60 to 100 meters in diameter, roughly the size of a football field. Yet, the energy released in its disintegration was apocalyptic, estimated to be equivalent to 10 to 15 megatons of TNT. That is about 1,000 times more powerful than the atomic bomb dropped on Hiroshima. Because the explosion happened several miles above the ground, the resulting fireball and blast wave radiated outward in all directions, creating that characteristic pattern of flattened trees with a standing, scorched center. The heat was so intense that it caused radiant burns and ignited fires across the taiga, while the shockwave traveled around the globe twice. The missing crater is therefore not a mystery at all, but the definitive signature of an airburst event. The object vaporized completely in midair, leaving no substantial fragments large enough to excavate a hole in the Earth. This understanding transforms Tunguska from a historical oddity into a sobering lesson in planetary defense. The event was a cosmic warning shot, demonstrating that an object too small to be easily detected with 20th century technology could still unleash the destructive force of a strategic nuclear weapon. Had the object's trajectory been different, arriving just a few hours later, it could have obliterated a major European city, with no one having any idea what was coming. The Tunguska airburst made it chillingly clear that the threat from space is not limited to global extinction-level events from giant asteroids. Smaller, yet still devastating, impacts are a real and recurring danger on a human timescale. This realization has directly fueled the modern effort to catalog all near-Earth objects large enough to cause significant regional damage, because what happened over Siberia in 1908 will inevitably happen again. The only question is when and where, and whether we will be watching the skies closely enough to see it coming, just when you think you've seen every kind of motion a space rock can perform. Our list brings us to number 17, a discovery that reveals some asteroids are essentially cosmic spinning tops pushed to their absolute limits. We're talking about rotation speed extremes, where these seemingly inert chunks of rock and metal are whirling around so rapidly they defy their own structural integrity. Some complete a full rotation in just a couple of minutes, spinning so fast that their own weak gravity is the only thing preventing them from flying apart entirely, while others are caught in a chaotic, wobbly tumble, rotating not around one stable axis, but tumbling end over end in a dizzying display of celestial instability. This isn't the gentle, predictable spin of a planet. This is motion pushed into the realm of the bizarre, and the force behind it is as subtle as it is relentless. The engine driving this incredible transformation is known as the Yarkovsky-O'Keefe-Radzievsky-Paddock effect, or YORP for short. It sounds complex, but the principle is beautifully simple. It's the subtle, cumulative push of sunlight. Imagine an asteroid drifting through space, its surface unevenly shaped with hills, ridges, and craters. As sunlight strikes this irregular surface, it's absorbed and then later re-radiated back into space as infrared heat. This re-radiation isn't just a release of energy, it carries with it a tiny, almost imperceptible amount of momentum. On a perfectly smooth, spherical object, these pushes would cancel each other out. But on a lumpy, asymmetric asteroid, they don't. Certain areas, depending on their shape and orientation, end up getting a slightly stronger push than others. Over millions of years, this tiny imbalance acts like a constant, gentle pressure on a celestial lever. For a slowly spinning asteroid, this persistent nudge can either accelerate or break its rotation, gradually speeding it up or slowing it down in a process that is incredibly slow but utterly unstoppable. The consequences of this slow-motion acceleration are nothing short of dramatic. Consider an asteroid shaped roughly like a spinning top. The Yorp effect can cause it to spin faster and faster over eons. As its rotation rate increases, the centrifugal force at its equator grows stronger and stronger. For a solid, monolithic chunk of iron, this might not be a problem. But for the more common rubble pile asteroids, those loose collections of boulders and dust we've discussed, this increasing spin creates an existential crisis. The centrifugal force trying to fling the material out into space begins to rival the asteroid's own meager gravity, which is the only force holding it together. The asteroid literally starts to struggle against itself, stretching at its equator and potentially triggering landslides as surface material migrates toward the bulging middle. In the most extreme cases, if the spin accelerates past a critical point, the asteroid can be torn in two, or it can begin to shed its outer layers, creating a cloud of debris, or even forming a small, secondary moon from the ejected material. The Yorp effect, therefore, is not just a curiosity, it's a fundamental sculptor, capable of reshaping and even breaking apart entire asteroids through the gentle, patient power of light. Then there are the tumblers asteroids that have succumbed to a different kind of rotational chaos. Instead of a clean, stable spin around a single axis, they are tumbling erratically, their rotation state constantly changing. This often happens after a significant trauma, like a glancing collision with another asteroid. The impact imparts a complex, off-center momentum that sends the object into a wobbling, unpredictable spin, much like a football fumbled in midair. The Yorp effect interacts with these tumblers in fascinating ways, sometimes working to stabilize them over immense timescales, or in other cases, exacerbating their chaotic motion. Observing these objects is a challenge for astronomers, as their changing orientation and brightness make them difficult to track and model, but they represent a crucial piece of the puzzle in understanding the dynamic life cycle of asteroids, showing us that their rotational histories are often as complex and violent as their cratered surfaces. The real-world evidence for this phenomenon is both compelling and visually striking. One of the best examples is the asteroid 2001 OE-84, a relatively small object about 700 meters across. Radar observations revealed it is spinning at a truly breathtaking rate, completing one full rotation every 29 minutes. That is so fast that at its equator, the centrifugal force is nearly strong enough to overcome its gravity. Any loose material on its surface would be flung off into space, and the entire body is likely under immense internal stress, stretched to its absolute limit. It is a world living on the edge of disintegration. On the other end of the spectrum, the asteroid 2008 E85 was found to be in a state of pure tumbling, its rotation so complex that scientists had to develop new mathematical models just to describe its motion. These are not theoretical possibilities. They are observed, measured realities that confirm the profound and long-term influence of solar photons on the evolution of our solar system's smallest bodies. Understanding these rotation extremes is far more than an academic exercise. It has direct and crucial implications for our future in space. If we ever plan to send spacecraft to land on an asteroid, either for scientific sampling or for future mining operations, the rotation state of the target is one of the most critical factors. Attempting to land on an object that is spinning rapidly or tumbling chaotically would be a navigational nightmare, dramatically increasing the risk of mission failure. The weak, shifting gravitational field around a fast, spinning rubble pile would make it incredibly difficult for a spacecraft to maintain a stable orbit or execute a precise touchdown. Furthermore, the process of rotational disintegration continually refreshes the asteroid's surface, exposing fresh material from within. This means that the regolith on a fast, spinning asteroid could be unexpectedly unstable, like trying to stand on a steep, ever-shifting sand dune. The study of Yorp-driven rotation is therefore essential practical knowledge, teaching us how to approach, navigate, and interact with these small worlds as we take our next steps toward becoming a spacefaring species. But the intrigue of asteroid Ryugu deepens far beyond its organic treasure trove, leading us to the 18th bizarre discovery on our list, the mysterious black goo itself. When scientists in Japan first opened the return capsule from the Hayabusa 2 mission and peered inside, they weren't greeted by the typical gray, rocky dust one might expect. Instead, they found a material of profound darkness, a fine-grained, carbon-rich substance so profoundly black it seemed to swallow light. Its appearance was startling, often described as a sticky, almost tarry black goo, a substance that looked less like celestial rock and more like something primordial and unformed. This was no ordinary asteroid sample. This was a direct shipment from the deepest past of our solar system, a material that had been kept in the ultimate deep freeze, completely untouched and unaltered for 4.5 billion years. The profound darkness of this material is a direct clue to its incredible composition. Its jet black color comes from an exceptionally high abundance of carbon, making up several percent of the sample by weight. To put that in perspective, most rocks on Earth contain only a tiny fraction of a percent of carbon. This isn't just simple graphite or diamond. It's a complex macromolecular carbon, similar to the insoluble organic matter found in the most primitive meteorites, but in a state of preservation that is far superior to anything we've ever held before. Intermixed with this carbon are tiny, beautiful grains of minerals like olivine and pyrrozine, but they are utterly dominated and darkened by the thick, pervasive carbon matrix that coats and binds everything together. This goo is the embodiment of the original cosmic dust cloud, the literal dark stuff from which the planets were first assembled, preserved in a pristine state that no Earth rock could ever hope to achieve. What makes the Ryugu samples so revolutionary is their absolute purity. Meteorites that fall to Earth are immediately contaminated. They plunge through our atmosphere, where they are scorched and altered, and then they sit on the ground, where they are exposed to water, oxygen, and terrestrial microbes, all of which slowly degrade and change their delicate primordial chemistry. The Ryugu material, however, was collected in the vacuum of space, sealed in a sterile container, and delivered directly to a pristine, clean room on Earth. It is the most uncontaminated sample of the early solar system humanity has ever possessed. This purity allows scientists to be confident that every measurement they take, every amino acid they identify, every isotopic ratio they calculate, is a true and unblemished record of conditions in the infant solar system, not a result of 4.5 billion years of terrestrial interference. The significance of this black goo, therefore, cannot be overstated. It acts as a definitive chemical benchmark, a baseline recipe for planet formation. By analyzing its exact chemical and isotopic makeup, scientists can now answer fundamental questions about the original ingredients that coalesced to form our Sun and all the planets. For instance, the specific ratios of different isotopes of elements like oxygen, nitrogen, and hydrogen in the Ryugu sample provide a unique fingerprint. This fingerprint can now be compared to the isotopic ratios found in different types of meteorites and even in the Sun itself. This allows researchers to trace the lineage of various planetary bodies back to their specific neighborhoods in the protoplanetary disk, essentially mapping out where different types of material originated and how they mixed together during the solar system's violent infancy. Furthermore, the physical nature of this dark, carbon-rich goo helps explain one of the great mysteries of the early solar system: how tiny dust grains managed to stick together to form the first pebbles. and then the first planetesimals. The carbonaceous material acts as a primordial glue. In the cold, dark nebula where the solar system formed, these sticky, organic, rich dust grains would have been far more effective at clumping together during low-speed collisions than pure, hard mineral grains would have been. This black goo was likely the adhesive that helped build the very first building blocks of planets, starting the cascade of accretion that ultimately led to worlds like Earth. Its presence on Ryugu shows us that the process of planet formation didn't begin with hard rocks smashing together, but with dark, sticky dust gently coalescing in the void, a slow and sticky start to the construction of our entire cosmic neighborhood. This unassuming black substance is, in effect, the missing link between the diffuse cosmic cloud and the solid, complex planets we know today, offering a humbling glimpse into our own deepest origins. And this leads us to the profound realization that the asteroid belt is not a random collection of individual rocks, but a vast, celestial family tree, complete with lineages and long-lost relatives. At number 19, we explore the concept of asteroid families and their spectral ghosts. Imagine a single, large parent body, perhaps a protoplanet hundreds of kilometers across, orbiting peacefully in the early solar system. Then, catastrophe strikes. A colossal impact with another massive object shatters it into thousands of pieces. These fragments don't just vanish, they inherit the parent's orbital path, traveling around the sun together as a flock of debris. Over time, the subtle gravitational nudges from planets, especially Jupiter, and the gentle, persistent push of the Yarkovsky effect cause these fragments to slowly drift apart. But they never completely forget their shared origin. Astronomers can identify these related groups, known as asteroid families, by looking for clusters of objects that share not only a similar orbit around the Sun, but also a strikingly similar composition, as revealed by their spectral signatures. It's like finding a group of people with the same rare eye color and the same unique surname, all living in the same neighborhood. The evidence for a common ancestor is overwhelming. The process of identifying these families is a masterclass in cosmic detective work. Scientists use powerful computers to analyze the orbital elements of hundreds of thousands of known asteroids, their average distance from the Sun, the tilt of their orbit, and its shape. When they plot this data, distinct clusters jump out. One of the most famous is the Vesta family, a huge collection of asteroids that were all blasted off the protoplanet Vesta by the immense impact that created the Resilvia Basin. We know this for a fact because we have meteorites on Earth that came from Vesta, and their mineralogy is a perfect match for the spectra of these family members. Finding a family like this is like discovering the scene of a historical crime, and then finding all the pieces of the murder weapon scattered around the room. It allows us to piece together the event itself, to understand the force of the impact, and to trace the diaspora of material that resulted from that single, defining moment of violence. But the story grows even more intriguing with the concept of ghost families. Time is the great eraser in the asteroid belt. Over billions of years, the steady gravitational perturbations and the Yarkovsky effect can act like a cosmic mixer, slowly scattering the members of a once tight family across a much wider volume of space. Their orbital paths become so randomized and dispersed that the initial cluster is no longer obvious. The family, for all intents and purposes, appears to have vanished into the background population of the belt. These are the spectral ghosts, the faint echoes of ancient collisions that are incredibly difficult to detect. Uncovering them requires sifting through the data with even more sophisticated tools, looking for subtle statistical groupings or compositional similarities that persist even when the orbital elements have diverged. Finding a ghost family is like trying to reunite a family that was separated centuries ago. Using only faded portraits and snippets of old stories, passed down through generations. It is detective work on a billion-year timescale. The significance of identifying these ghost families is immense. They hold the key to understanding the asteroid belt's true history of violence. The number of families we can see today represents only the most recent major collisions, those that happened in the last billion years or so. The older the collision, the more its fragments will have been scattered, eventually becoming undetectable as a coherent group. By developing methods to find these ancient ghosts, astronomers can peer much further back in time, creating a more complete census of the cataclysmic events that have shaped the main belt. This, in turn, tells us about the population of objects that existed in the early solar system. A belt filled with the ghosts of many large families suggests an era of tremendous bombardment, with many large protoplanets being shattered. A belt with fewer ghosts might indicate a slightly less violent, or perhaps more efficient, accretionary period. These spectral families are therefore the missing chapters in the history book of our solar system's formation. This understanding completely transforms our view of the asteroid belt from a static collection of rocks into a dynamic, evolving ecosystem. It is a place where families are born in moments of shattering violence, and then slowly, over eons, are scattered to the cosmic winds, their identity fading until only the most patient scientific scrutiny can hope to resurrect them. Every asteroid, from the largest like Ceres to the tiniest speck, is a piece of a larger puzzle. Some pieces are still huddled together, telling a clear story of a recent breakup. Others are lone wanderers, their family connections long since erased by time, holding secrets of collisions so ancient they occurred when life on Earth was still in its most primitive, single-celled infancy. The study of asteroid families and their ghosts is ultimately a search for our own cosmic genealogy, tracing the lineage of the rubble from which our own planet was built, one fragmented family at a time. Now we arrive at a peculiar process that acts like a cosmic spray tan, slowly but surely changing the very face of an asteroid over immense stretches of time. At number 20 on our list, we explore the bizarre phenomenon of space weathering. Imagine leaving a beautiful, shiny new car parked outside, not for a few years, but for millions of years, exposed to relentless dust storms and a constant, invisible sandblaster. The pristine paint would quickly become faded, pitted, and stained. A similar, though far more alien, process is constantly at work on the airless surfaces of asteroids, subtly transforming their appearance, and in doing so, actively hiding their deepest secrets from our prying eyes. The primary artists behind this cosmic renovation are twofold. First, there is the solar wind, a never-ending stream of charged particles, mostly protons and electrons, that flows outward from the sun at speeds of over 1,000,000 miles per hour. Without a protective magnetic field or atmosphere to deflect it, this torrent of radiation constantly bombards the surface of an asteroid. Second, there are micrometeorites, countless tiny specks of dust and grain-sized particles traveling at breathtaking speed. These aren't the dramatic, crater-forming impacts of larger asteroids. This is a perpetual, gentle rain of microscopic bullets that slowly but surely grinds away at the surface. Individually, each particle is insignificant, but over hundreds of millions of years, their cumulative effect is profound, creating a layer of alteration that completely changes how the asteroid reflects light. The most visible results of this process are a darkening and a reddening of the surface. The darkening occurs because the relentless bombardment from the solar wind and micrometeorites creates microscopic layers of tiny iron nanoparticles. These nanoscale bits of metal form when the intense energy from impacts and radiation vaporizes iron-bearing minerals in the surface rocks, and then that vapor condenses back into a fine, dark coating that literally stains the regolith. Think of it as a cosmic mist of iron dust settling over everything. At the same time, the spectrum of the reflected light shifts toward the red end. This reddening happens because the smaller, nanoscale particles left behind by the weathering process scatter and absorb blue light more efficiently than red light, giving the asteroid a ruddy, reddish tint when viewed through our telescopes. This creates a monumental problem for astronomers trying to understand these distant worlds. From our vantage point on Earth, we rely almost entirely on spectroscopy, analyzing the light reflected off an asteroid to determine what it's made of. We have a library of spectral fingerprints for pristine, unweathered minerals, but when space weathering darkens and reddens an asteroid's surface, it effectively disguises its true spectral signature. A weathered asteroid can look remarkably similar to a completely different type of asteroid that just happens to be naturally dark and red. It's the ultimate case of mistaken identity, where a common stony asteroid could be misclassified as a rare, carbon-rich type, or vice versa, simply because we're only seeing its heavily weathered outer skin and not the fresh material hiding just beneath. The game-changing evidence for this came from a direct comparison that only space missions could provide. For years, telescopic observations of the asteroid Eros suggested its surface composition was different from the most common meteorites found on Earth, known as ordinary chondrites. This was a major puzzle, as we expected many asteroids to be the source of these common meteorites. The mystery was solved when the Near-Shoemaker spacecraft orbited Eros and analyzed its surface in exquisite detail. The spacecraft's instruments could peer past the superficial weathering and revealed the asteroid's true composition. The data was a perfect match for ordinary chondrites after all. The discrepancy wasn't in the rock itself, but in the dark, reddened crust that space weathering had painted over it. Our telescopes on Earth had been fooled by a cosmic veil that the spacecraft, flying up close, could simply look through. This revelation forces us to completely reconsider our entire catalog of asteroid classifications. Much of what we thought we knew about the distribution of different materials in the asteroid belt is based on those weathered, surface-level observations. It's possible that the belt is far more uniform in composition than it appears, with many asteroids looking different from one another only because they have experienced varying degrees of this space weathering process. An asteroid's location, its age, and even its specific orbit can all influence how much solar wind and micrometeorite bombardment it has endured. This means two asteroids made of the exact same material could have wildly different appearances if one has been dwelling in a more exposed region of the belt for a longer period of time. Understanding space weathering isn't just about correcting a minor error. It's about recalibrating our fundamental map of the solar system's building blocks, forcing us to see past the cosmetic changes to understand the true geology lying in wait underneath. Sometimes, the most shocking discoveries aren't made in the distant, silent void of the asteroid belt, but right here in our own skies, in a flash of light and sound that brings the reality of cosmic impacts terrifyingly close to home. At number 21 on our list, we revisit an event that was witnessed by millions, the Chelyabinsk meteor of 2013. On a clear winter morning over Russia, a brilliant fireball, brighter than the sun, streaked across the sky, followed moments later by a powerful shockwave that shattered windows, damaged buildings, and injured over 1,000 people, mostly from flying glass. It was a stark reminder of our planet's vulnerability, a cosmic alarm clock that rang with the force of nearly 500 kilotons of TNT. In the immediate aftermath, the world focused on the singular, spectacular fireball captured on countless dashcams. But as scientists meticulously pieced together the data in the weeks and months that followed, a far more bizarre and complex story began to emerge, a story suggesting that the asteroid that shook Chelyabinsk may not have been traveling alone. The initial analysis of the countless video recordings allowed researchers to triangulate the object's trajectory with incredible precision. They traced its path back into space, revealing it came from the Apollo family of near-Earth asteroids, on an orbit that brought it around the Sun and into a fateful collision course with Earth's atmosphere. The object was estimated to be about 20 meters in diameter before it entered, a sizable chunk of rock, as it plunged into the atmosphere at a shallow angle of about 18 degrees and a speed of nearly 19 kilometers per second. The immense pressure and heat began to tear it apart. The intense brightness of the fireball, or its peak luminosity, occurred at an altitude of about 29.7 kilometers above the ground. This is the moment when the bulk of the object violently disintegrated, releasing the majority of its immense kinetic energy in a blinding flash. It was this explosion that created the powerful shockwave that later reached the city of Chelyabinsk. However, when scientists from the Czech Academy of Sciences delved deeper into the data, they noticed something peculiar. Their sophisticated computer models, which simulated the breakup of the asteroid, indicated that the observed path of the main fireball and the subsequent distribution of the shockwave damage on the ground could not be perfectly explained by a single monolithic object. There seemed to be a discrepancy. To account for the full pattern of the event, their models strongly suggested that a second, smaller object had entered the atmosphere alongside the main asteroid. This hypothetical companion was estimated to be several meters across, a fragment traveling a slightly different path. It would have entered the atmosphere just before the main body, disintegrating at a higher altitude, around 38 to 45 kilometers up. This earlier, smaller airburst would have contributed its own energy to the overall event and helped shape the complex shockwave pattern that ultimately caused the widespread damage. This theory of a hidden companion transforms the Chelyabinsk event from a simple, if dramatic, meteor airburst into a glimpse of a much more complex and dynamic reality. It suggests that the asteroid that threatened a modern city was not a lone wanderer, but quite possibly part of a binary or multiple system, a smaller moon orbiting a larger primary body, just like the systems we've observed in the main belt. As the pair approached Earth, our planet's gravity would have gently shepherded them, potentially altering their relative trajectories just enough so that they entered the atmosphere a few seconds and a few kilometers apart. This isn't just a wild guess. We have direct evidence that such systems exist and can interact with Earth. In 2020, a small meteoroid named EN 2020-20X3 was observed by a global network of cameras breaking up over the Czech Republic. The analysis revealed it was part of a stream of meteoroids, a string of cosmic pearls, all following the same orbit. This proved that small, co-orbiting clusters do indeed enter our atmosphere, providing a tangible precedent for the Chelyabinsk companion theory. The implications of this are profound for planetary defense. The Chelyabinsk event was a complete surprise. The asteroid came from the direction of the Sun, completely hidden in the glare, and was far too small to be detected by existing surveys at the time. The idea that such an unseen threat could potentially be a double impact or a clustered impact adds a new layer of complexity to the hazard. Our defense strategies, which often focus on tracking and deflecting a single large object, would need to account for the possibility of a primary target accompanied by one or more smaller, yet still dangerously energetic, companions. A deflection mission that successfully nudged a large asteroid might inadvertently leave a trail of smaller, untracked fragments on a collision course, turning a single bullet into a shotgun blast. Understanding the binary nature of some asteroid populations is therefore not an academic exercise. It is a critical part of accurately assessing the true risk profile of any potential impactor. While a larger fragment of the main Chelyabinsk body plunged into Lake Chebarkul, leaving a hole in the ice and later being recovered from the muddy bottom, no substantial physical evidence of the proposed companion has been found. This is not surprising, as the smaller object would have likely vaporized completely at its higher altitude of disintegration, leaving no meteorites behind. Its existence remains inferred from the sophisticated forensic analysis of the event's physics, a ghost in the machine of the atmospheric entry data. Yet, this very inference makes the Chelyabinsk event a pivotal case study. It serves as a powerful, real-world example of how our understanding of asteroids is constantly evolving, forced to adapt by new data and new perspectives. What we witnessed that day was not just a random rock from space, but potentially a tiny, shattered solar system in its own right, a primary body and its moon, ending their 4.5 billion-year journey in a dramatic final act over Russia, reminding us that the sky above holds complexities we are only beginning to fathom. And now we arrive at number 22 on our list, a discovery that unfolded in real time and forced a team of brilliant scientists and engineers to completely rewrite their playbook. This is the story of asteroid Bennu's surprising surface, a finding that transformed what was supposed to be a straightforward touchdown into a heart-pounding, high-stakes maneuver. Before the osiris-rex spacecraft arrived, the best data suggested Bennu would have a relatively smooth terrain, covered in fine-grained sandy or gravel-like material. Mission planners envisioned wide, welcoming plains, perfect for the spacecraft's sampling mechanism to gently touch down and collect a pristine sample. But as the probe drew closer and its cameras began to resolve details on the surface, a collective gasp likely went through the control room. Bennu was not a smooth, sandy beach. It was a treacherous, chaotic world, an immense rubble pile littered with so many boulders that it was difficult to even spot a clear patch of ground. The asteroid looked less like a collected object and more like a pile of construction debris dumped in space, with house-sized rocks jutting out at all angles, creating a landscape of incredible peril. This unexpected reality posed an immense and immediate challenge for the mission's primary goal, the touch-and-go sample collection maneuver. The spacecraft was designed to descend slowly, extend its robotic sampling arm, and upon contact, release a burst of nitrogen gas to stir up surface material, which would then be captured in the collection head. This entire delicate ballet was predicated on touching a smooth, stable surface. A direct hit on one of the countless large boulders could have damaged the sampling arm, tipped the spacecraft over, or simply failed to collect any material at all. The team suddenly found themselves staring at a cosmic parking lot filled with jagged rocks, needing to find a single, car-sized parking spot that was perfectly smooth and safe. They had to go back to the drawing board, spending months using the spacecraft's own high-resolution imagery to meticulously map every single boulder and every potential hazard across the entire surface of Bennu, searching for a safe haven in a world of rock and shadow. The search for a suitable sampling site became a monumental effort in itself, a testament to human ingenuity and persistence. The mission team, originally expecting to have a wealth of easy options, found themselves with almost none. They ultimately identified two primary candidate sites, nicknamed Nightingale and Osprey, but even these were far from ideal. Nightingale, the primary site, was nestled within a small crater in Bennu's northern hemisphere. While it offered the finest grain material, it was surrounded by a veritable wall of dangerous boulders, like trying to land in a stadium surrounded by skyscrapers. The margin for error was terrifyingly small. To ensure success, the team had to develop and upload new, highly advanced navigation software to the spacecraft, giving it a level of autonomous hazard recognition and avoidance that had never been attempted before on such a scale. The spacecraft would have to compare real-time images of the approaching surface with its onboard map during the final descent, and if it detected a hazard larger than a small coffee table, it was programmed to autonomously abort the touchdown and back away. This was no longer a simple pickup. It was a high wire act over a pit of razor-sharp rocks. The successful touchdown in October 2020 was a breathtaking feat of engineering, a moment of pure triumph over a deeply challenging environment. As the spacecraft descended, its camera captured stunning, close-up images of the surface, revealing a landscape so loosely packed that the sampling head appeared to sink into it, sending a plume of rocks and dust shooting outward. The surface material responded not like solid rock, but like a fluid, a clear indication that Bennu is indeed a rubble pile with virtually no cohesive strength, held together by the faintest whisper of gravity. The maneuver collected so much material, in fact, that the sample container's lid was jammed open by larger rocks, allowing some of the precious cargo to slowly escape into space before the container could be safely stowed, a bittersweet problem that underscored both the abundance of the surface material and its unexpectedly coarse, rocky nature. Yet, from this immense operational challenge came unexpected and profound scientific rewards. The very boulders that made the landing so difficult turned out to be the keys to unlocking Bennu's deepest history. The analysis of the returned samples, combined with the detailed orbital data, revealed that Bennu is not just a simple pile of rubble. It is a carbon-rich time capsule, absolutely packed with water-bearing clay minerals and a complex array of organic molecules, including key building blocks for life like carbon and amino acids. The boulders themselves are not uniform. They show a wide variety of compositions and textures, suggesting they originated from different depths within a much larger, water-rich parent body that was destroyed in a catastrophic collision billions of years ago. Bennu, therefore, is not a single asteroid, but a collection of fragments from a lost world, a shattered protoplanet that once had the conditions necessary for complex chemistry. The treacherous, boulder-strewn surface, once seen as an obstacle, is now recognized as a rich and diverse geological archive, preserving pieces of that ancient parent body that we would never have had access to on a smoother, more homogenized world. The very difficulty of the sample collection forced a deeper engagement with the asteroid's true nature, revealing that sometimes the most valuable scientific treasures are found not on the easy paths, but hidden among the most daunting rocks. Just when we think we've established clear categories in our solar system, it reveals yet another class of object that defies all our attempts at simple classification. At number 23 on our list of bizarre asteroid discoveries, we encounter the solar system's ultimate cosmic nomads, the centaurs. These are not solitary rocks of the inner belt or icy visitors from the distant Oort cloud. They occupy a vast and turbulent realm between the orbits of Jupiter and Neptune, behaving with a baffling duality that has earned them their mythological name, a fusion of two natures, neither fully one thing nor the other. A centaur might look like a simple asteroid one moment, a dormant, rocky body, and then, as it journeys closer to the sun, suddenly flare to life, displaying the fuzzy coma and tail of a comet. This schizophrenic behavior is a direct result of their incredible, chaotic orbits, paths so unstable and unpredictable that they are rewriting our understanding of the solar system's gravitational dynamics and its early history. The defining characteristic of a centaur is its wild, often short-lived orbit. Unlike the relatively placid, near-circular paths of planets or the organized ellipses of many main-belt asteroids, centaur orbits are profoundly unstable, crossing the paths of the giant planets. They swoop in on highly eccentric, tilted paths that bring them from the frigid outer darkness near Neptune's orbit to the warmer realms closer to Jupiter, and then back out again. This existence is a celestial tightrope walk through the most gravitationally violent neighborhood in the solar system, with every pass near a gas giant, especially Jupiter or Saturn. A centaur receives a powerful gravitational kick, a slingshot effect that dramatically alters its trajectory. Some are flung inward to become Jupiter family comets, destined for repeated close encounters with the Sun. Others are hurled outward, back into the deep freeze, or even ejected from the solar system entirely. A single orbit for a centaur is a journey through a cosmic pinball machine, with the massive planets acting as the flippers, constantly batting these objects into new and unpredictable paths. This inherent instability means that no centaur's current orbit is its permanent home. They are all just passing through, temporary residence in a gravitational war zone. So, where did these celestial hybrids come from? The most compelling theory paints them as refugees, pilgrims from a distant and frozen frontier. Scientists widely believe that centaurs are escapees from the Kuiper Belt, that vast disk of icy bodies that begins beyond Neptune's orbit. In the gravitational chaos of the early solar system, the giant planets migrated, their shifting gravity stirring up the pristine Kuiper Belt like a spoon swirling a cup of coffee. This perturbation sent countless icy planetesimals scattering inward into the realm of the giant planets. These inward-bound Kuiper Belt objects became the centaurs we observe today. They are the lucky ones that didn't crash into a planet or get flung into interstellar space. They are the survivors of that ancient planetary shake-up, caught in a gravitational purgatory that will ultimately decide their final fate. This makes every centaur we study a precious messenger, a direct sample of the primordial material from the outer solar system, delivering to our doorstep the very ice and rock that built planets like Uranus and Neptune. This refugee status gives centaurs an immense scientific value that far outweighs their relatively small numbers. By studying their composition, we are conducting a remote geological survey of the Kuiper Belt without having to send a spacecraft all the way out there. When a centaur becomes active, venting gases and dust as it approaches the Sun, its coma acts like a laboratory bell jar, releasing volatile compounds that have been locked in a deep freeze for 4.5 billion years. Spectroscopic analysis of this material reveals a cocktail of ices, including water, carbon monoxide, carbon dioxide, and even more complex hydrocarbons. This chemical inventory is a frozen record of the conditions in the protoplanetary disk where the outer planets formed, allowing us to test our models of solar system formation against real, observed data from its farthest reaches. Each active centaur is a temporary, self-displaying exhibit of outer solar system chemistry, offering a glimpse into the raw ingredients that were available to build the icy moons and dwarf planets of the Kuiper Belt. The most famous and dramatic example of a centaur's dual nature is the object Chiron, discovered in 1977. Chiron was initially classified as an asteroid due to its orbit between Saturn and Uranus. For years, it was considered the largest known asteroid, a title it held until the discovery of many larger Kuiper Belt objects. But then, in the late 1980s, something extraordinary happened. Astronomers watched in astonishment as Chiron suddenly brightened and developed a faint, cometary coma. This dormant giant, over 200 kilometers in diameter, had awakened. It was outgassing, proving definitively that it was not a dry, rocky asteroid, but an icy body, a comet on a colossal scale. Chiron's activity is thought to be driven by the sublimation of highly volatile ices, like carbon monoxide or nitrogen, which can turn directly from solid to gas at the much colder temperatures of its distant orbit. Its behavior is a perfect case study in the transitional nature of these objects, a massive planetary building block caught in the act of evolving from a quiet Kuiper Belt relic into an active, sun-warmed comet. Studying these objects is a race against time, not just because their orbits are unstable, but because their very nature is fleeting, as a centaur is repeatedly tugged inward by the gravity of the giant planets. The increasing solar radiation cooks off its more volatile ices. With each orbit, it loses a little more of its primordial essence, building up a crust of dust and non-volatile material on its surface, a process known as forming a rind. This crust can eventually seal in the remaining ices, shutting down the outgassing activity and making the object appear, for all intents and purposes, like a dead, rocky asteroid. A centaur we observe today as active might be dormant in just a few thousand years, its internal secrets hidden beneath a sterile, dark surface. This means we are catching them in a brief, dynamic phase of their multi-billion-year life cycle, a transitional period that offers a unique window into the processes that turn icy planetesimals into the dormant cometary nuclei and dark asteroids of the inner solar system. The centaurs are not permanent members of our planetary system. They are transient visitors on a grand cosmic journey, and we are fortunate to be here at just the right time to witness their spectacular and often bizarre passing. But while we're contemplating the grand journeys of objects like centaurs, our next discovery brings our focus down to an almost impossibly small scale, revealing a treasure hidden within the primitive meteorites that land on our planet. At number 24, we encounter one of the most profound and humbling findings in all of planetary science: prosolar grains. These are not merely ancient, they are truly alien, microscopic dust particles that formed not in our own solar system, but in the fiery deaths and outflows of other stars that lived and died long before our sun was even a glimmer in a cosmic cloud. When you hold a meteorite rich in these grains, you are literally holding pieces of other suns, the preserved building blocks from which our entire cosmic neighborhood was ultimately assembled. Finding these grains is a monumental challenge, a needle in a haystack search of epic proportions. They are incredibly tiny, most measuring only a few micrometers across, far smaller than the width of a human hair. And they are exceedingly rare, making up less than 1,000% of the most primitive meteorites. To locate them, scientists perform a kind of cosmic alchemy, taking a meteorite sample and dissolving it in some of the strongest acids known, acids that can eat through glass and metal. These harsh chemicals are not a destructive force in this case, but a refining one. They carefully dissolve away the 99.99% of the meteorite that formed in our own solar system, leaving behind only the most stubborn, resilient minerals, the diamonds, silicon carbide, and graphite that constitute the prosolar grains. These tiny, indestructible time capsules survive the acid bath, allowing researchers to isolate them and study their individual atomic secrets. It is within the atoms of these grains that their incredible extraterrestrial origin is proven beyond any doubt. Every element has different versions, called isotopes, which have the same number of protons, but a different number of neutrons in their nucleus. The ratios of these isotopes are like a star's unique signature. In the well-mixed, homogenized environment of our solar system, most materials have a very consistent isotopic ratio. But when scientists analyze prosolar grains, they find isotopic ratios that are wildly abnormal, completely off the charts compared to anything native to our solar system. For instance, a grain might be almost pure in a specific isotope of neon or xenon that could only have been produced under the extreme, specific conditions inside a particular type of dying star. These anomalous signatures are the definitive proof that the grain is a literal piece of stardust, a refugee from a stellar environment entirely separate from our own. Different types of stars leave behind different kinds of dust, each with its own dramatic creation story. The most common prosolar grains are tiny diamonds, each nanocrystal containing only a few thousand carbon atoms. These are thought to have condensed in the outer atmospheres of cool, red giant stars, gently drifting away like cosmic soot. Then there are the larger grains of silicon carbide, which form in a more violent setting, the envelopes of asymptotic giant branch stars, which are sun-like stars in their final, turbulent throes of life. But perhaps the most dramatic origin story belongs to grains that come from supernova, the colossal explosions of massive stars. These grains contain elements like silicon, oxygen, and even aluminum that were forged in the unimaginable heat and pressure of the supernova blast itself, and then flung out into the galaxy at incredible speeds. Each type of grain is a messenger from a different kind of stellar death, carrying a specific chemical record of its parent star's final moments. This discovery fundamentally transforms our understanding of our own origins. We are not just children of our sun. We are the children of countless stars. The very iron in your blood, the calcium in your bones, and the oxygen you breathe were all forged in the nuclear furnaces of long-dead stars. Prosolar grains provide the tangible, physical evidence for this incredible concept. They are the surviving seeds from that stellar diaspora, the actual material that was floating in the interstellar medium when a nearby supernova shockwave triggered the collapse of our own solar nebula. These grains were the original condensing points, the seeds around which the first dust and ice of our solar system began to clump together, starting the process that would eventually lead to the formation of asteroids, planets, and us. Holding a prosolar grain is therefore an act of touching deep time and vast space simultaneously. These microscopic specks have endured an almost incomprehensible journey. They were born in the heart of a star billions of years ago, were blasted across light years of interstellar space, drifted into the cloud that became our solar system, were incorporated into an asteroid where they waited, undisturbed, for 4.5 billion years, and then survived a fiery fall to Earth to end up under a scientist's microscope. Their resilience and their message are equally powerful. The universe is deeply interconnected, and we are made from the ashes of its most majestic and cataclysmic events. They are the ultimate heirlooms, proving that our cosmic genealogy stretches back far beyond the birth of our own sun, connecting every one of us to the grand life and death cycle of the stars themselves. And now we conclude our countdown with what might be the most visually strange and enduring geological puzzle of all, a set of features that look like they were carved by an invisible sculptor. At number 25, we have the bizarre and mysterious pits on asteroid Eros. When the near-Shoemaker spacecraft arrived at Eros in 2000, it revealed a world scarred by craters and littered with boulders, but it was the presence of about 250 strange, flat-floored depressions that truly captivated scientists. These weren't your typical impact craters, which are generally bowl-shaped and have raised rims. These pits were different. They were remarkably circular, with sharply defined vertical sides that dropped down to perfectly smooth, flat floors, almost as if someone had taken a giant cookie cutter and punched neat, cylindrical holes directly into the asteroid's surface. Their unnatural geometry immediately signaled that something other than a simple impact was at work here, a process unique to the low-gravity, airless environment of a small world. The leading theory to explain these enigmatic features points to a process of subsurface outgassing, a slow and silent burp from within the asteroid itself. Imagine Eros not as a completely dead rock, but as a body that still holds volatile compounds, or perhaps water ice, carbon dioxide, or other frozen gases locked away in pockets just beneath its dusty surface. Over billions of years, the faint but constant heat from the sun would very slowly warm these buried deposits. In the vacuum of space, this warming wouldn't create liquid. Instead, the ices would sublimate, turning directly from a solid into a gas. This transformation creates pressure, and as that pressure builds within the porous, rocky matrix, it searches for a way out. Eventually, the gas finds a weak spot in the overlying rock and dust, and it vents explosively into space. This sudden release would blow away the surface material, creating a clean, sharp-edged pit and scattering the excavated debris as a thin layer of fine dust around the rim. The perfectly flat floor is what's left behind after the gas has escaped, a stable, undisturbed layer of the asteroid's interior, now exposed to the void. But there is a compelling alternative, a theory that relies not on internal forces, but on external violence. This is the idea of seismic shaking, where the entire asteroid is jolted like a cosmic bell. When a large object slams into Eros, the energy from the impact doesn't just create a single crater. It sends powerful seismic waves rippling through the entire body. For a rubble pile asteroid like Eros, which is essentially a loose collection of boulders and dust held together by the faintest gravity, these shockwaves can be transformative. The vibrations would fluidize the surface regolith, causing the finer dust and grains to behave like a liquid. In this unsettled state, the finer material would naturally begin to sink, sifting down through the gaps and pores between larger, more resilient boulders. The result would be a process of segregation, where the large rocks are left exposed on the surface, and the fine dust drains away to collect in a smooth, level layer at the bottom of pre-existing topographic lows, effectively creating those flat-floored pits. In this scenario, the pit isn't excavated from above by an explosion, but is filled from below by a draining of material, a settling of the cosmic sediment after a major planetary tremor. So, how do we decide between a pit formed by a burp of gas and one formed by a settling of dust? The clues are in the details, and for Eros, the details are frustratingly ambiguous. If the outgassing theory is correct, you would expect to find clear evidence of the ejected material, a blanket of fine debris surrounding the pit, perhaps with a pattern that suggests an explosive venting event. While some pits on Eros do have surrounding deposits, the evidence isn't consistent or dramatic enough to be conclusive. On the other hand, the seismic shaking model would predict that the flat floors should be composed of exceptionally fine-grained material, much finer than the surrounding terrain. The near-Shoemaker data suggested the floors were indeed smooth, but definitively proving their composition as fine dust from draining was beyond the mission's capabilities. This lack of a definitive smoking gun is precisely what keeps the mystery alive today. The pits on Eros present us with two equally plausible, yet completely different geological histories, and with the data we have, we simply cannot choose one over the other with absolute certainty. The enduring puzzle of Eros's pits is more than just an academic curiosity. It highlights a fundamental gap in our understanding of how small, airless bodies evolve. These features are a testament to the fact that asteroids are not static museums of the past. They are dynamic worlds, subject to a slow, subtle geology driven by processes we are only beginning to comprehend. Whether through the slow buildup of internal gases or the sudden, planet-wide jolt of an impact, Eros is clearly capable of reshaping its own surface in ways that leave no clear, singular fingerprint. This mystery forces us to look at other asteroids with new eyes, searching for similar pits and wondering if the same forces are at work elsewhere in the solar system. The bizarre, cookie-cutter holes on Eros stand as a final, humbling reminder that even after we have mapped a world in exquisite detail, it can still hold onto its deepest secrets, challenging us to keep looking, keep questioning, and keep exploring the strange and wonderful mechanics of our cosmic neighborhood. And so, our journey through the asteroid belt and beyond reveals a solar system far stranger and more dynamic than we ever imagined. We began with the simple, foundational discovery of water ice, a finding that rewrote the narrative of our own planet's oceans and pointed toward a future of cosmic refueling stations. From there, we delved into the profound implications of complex organic molecules on asteroids like Ryugu, the very building blocks of life delivered to a primordial Earth, suggesting that our biological origins may be deeply intertwined with these nomadic rocks. We encountered the ghostly whispers of ancient magnetic fields locked in meteorites, telling tales of shattered protoplanets with molten metal hearts, and we navigated the fragile, unpredictable terrain of rubble piles that defy our best planetary defense strategies. We marveled at metallic worlds like Psyche, the exposed cores of failed planets, and watched as binary asteroids performed their silent, gravitational dances. We witnessed the hybrid nature of active asteroids, blurring the line between rocky relic and icy comet, and we mapped the bizarre, misshapen forms sculpted by eons of violent collisions. The cryovolcanoes of Ceres showed us that even small worlds can have slushy, restless interiors, while the interstellar visitor Oumuamua challenged our very definitions and hinted at the exotic materials born around other stars. From the gentle sorting of dust on Itokawa to the explosive airburst over Tunguska, from the frantic spins driven by sunlight to the pristine black goo of our solar system's birth, each discovery has systematically dismantled the old image of asteroids as simple, inert stones. They are instead time capsules, construction sites, chemical factories, and potential threats, all rolled into one. This incredible diversity of bizarre findings does more than just fill a list. It fundamentally reshapes our understanding of our cosmic home. The asteroid belt is not a barren junkyard. It is a living archive of the solar system's most violent and creative moments. It tells a story of planetary birth and destruction, of ingredients mixed and delivered, and of processes that continue to reshape these worlds right before our eyes. Every strange shape, every unexpected molecule, and every anomalous orbit is a clue in the greatest detective story of all, the story of how we came to be. These discoveries humble us, reminding us that Earth is not an isolated oasis, but a participant in a much larger, interconnected system, where the raw materials for life and the forces of creation and destruction are woven into the fabric of space itself. Now, the conversation turns to you. With 25 of the most mind-bending discoveries laid out, which one reshaped your view of the cosmos the most? Was it the revelation that Earth's water may have arrived on these ancient rocks, or the tantalizing possibility of mining precious metals from a world like Psyche? Were you captivated by the idea of interstellar visitors like Oumuamua, or the sheer, dynamic weirdness of an asteroid spontaneously spouting its own particles into the void? Let us know in the comments below which finding amazed you the most and why. We read every single one. If this deep dive into the mysteries of our solar system captivated you, there is so much more to explore. The universe is filled with enigmas waiting to be unraveled, from the hidden oceans of distant moons to the nature of dark matter itself. Make sure to subscribe and hit the notification bell so you don't miss our next journey to the frontier of discovery. Thank you for watching, and keep looking